the director in the research office, the manager in the research office, and all the team from research office who said this thing like this, thing like this. It's really appreciated. It's a good work. And also like great academics who are supporting this event, and our postgraduate students. Indeed, we are here because of them. We cannot do it without them. We love them. So I've said mine is just to introduce our keynote speaker. He is a professor in the Department of Chemistry at University of Zululand. He obtained his BSc honors from University of Natal, South Africa in 1994, and PhD from Imperial College, London, UK in 2000. He has published over 275 articles and 35 book chapters. Indeed, we lead people of this country. I think so for the first time, 275 articles and 35 book chapters. He has more than 6,500 citations with a high index of 40. He has given more than 85 lectures at national and international conferences. The research focus of Chair is on developing routes for delivery on the high quality functional material. The current focus is on each abundant material using material complexes and single source results via solvent, hot injection, and chemical vapor disposition route. The functional materials are used for application in energy generation and storage. Colleagues, allow me to call upon Prof. Navarrete to come to the stage.
Thank you, colleagues. My pleasure to speak here at this meeting. As the speaker announced, I've given many talks all around the world, but I've been at UniZulu since 1996, and I think this is only my third talk at UniZulu. So I've been very scarce in my institution, but it's a great pleasure to speak here at this meeting organized by the Research Office. Especially Prof. Brown and his team have worked tirelessly to promote research and innovation at the university. What I will speak about is work that we've been doing. Well, we started this work in nanotechnology at UniZulu in the year 2000. When I came back for my PhD at Imperial College, I started a research group at UniZulu. And what I'll present today is work done in the past 5 years. And this has been the most interesting 5 years of my career, most productive 5 years, and the most impactful 5 years. But I will start the talk with some background on nanotechnology and where it fits within the technology in the world, and how it came about, and how our work contributes to this field. So the title is Nanotechnology at UniZulu, because I'll speak mainly of what we are doing at UniZulu. The second part of the talk is more technical. Hopefully, we won't lose you. But I'll give you a flavor of what we are doing at UniZulu and why we are doing it, and where does it fit in within the overall context of research in the world. And to show you that we are actually competing at the international level. And that's something to be proud of, being a small university in a rural setting. Forward. Go forward. Okay, thank you. So where does nanotechnology come from? Where does it originate? there are three main landmarks, you may call it, in terms of the history. Actually, it's not a new technology. It's been around for many centuries. The Lycurgus cup shown on the right was 4th century AD by the Romans, and it was formed, or it showed that it could turn two colors, red and pink, depending on the light shone on it. And that was due to the gold colloids that were in the cup. So that was the first, it was noted as the first instance of nanotechnology. However, if you go back later in the 18th century, Michael Faraday made gold, and these are the samples of gold at the British institution in London, where he showed that you could make very small particles of gold, and those samples were analyzed later using the electron microscope. But the main, or the kind of roots of nanotechnology lies with the famous lecture by Richard Feynman in 1959, where he gave an idea of life in the future in his most famous lecture, The Study Room at the Bottom, which you can find on the internet. And there he made a prediction, and he prophesied that it would be possible in principle to make machines at the nanoscale that arrange atoms the way we want and do chemical synthesis by mechanical manipulation. And that's what we do now. We basically manipulate atoms at the nanoscale and design new properties for materials. So nanotechnology is not a field that belongs to, it's a multidisciplinary field. It involves chemistry, biology, physics, engineering, and it's only become popular due to other technologies that were possible. So the scanning tunneling microscope and the atomic force microscope allowed us to view atoms at the nanoscale. So that paved the way for future technology. This slide, it basically describes everything what we do. So we work in the area of 1 to 100 nanometers of particles, and we work on changing the size, the shape, and the assembly. And more importantly, on the left, you have composition change. So we can make various materials with varying compositions. We can change the composition by doping. And so the periodic table is our toolbox. And I always like to say we farm the periodic table. So within the periodic table, you have all your elements, and you can choose the elements that you want to work in with the properties that you desire. And you can manipulate the properties, and you can manipulate the size. And most importantly, you can change the assembly to create new materials. So that's what we do. Just as a background, more history. In 2023, this year, the Nobel Prize in Chemistry was awarded to 3 gentlemen who were involved in making quantum dots, which are nanomaterials which have quantum properties. So the Bras, Buwendi, and Ekimov partnership. Buwendi is actually Munji Buwendi is actually has African roots. He's a Tunisian, born in Tunisia, went to MIT. And in the late 90s, when I was a student in Imperial College, we were actually competing with his group, working on cadmium sulfide and selenide. So what did they discover? They discovered that you could change the size of the material, and you can vary the property. So the property that we're looking at is the absorption and emission properties. And I'll show you that in the next slide, why that happens. So this is some physics. Here you can see that in a material, in a semiconductor. So what's a semiconductor? It has a valence band and a conduction band. You have metals, which have a small band gap. You have insulators, which have a large band gap. And you have semiconductors, which have a variable band gap. So the band gap depends on the temperature. So as you increase the temperature, the band gap will vary. because you have you excite the electron from the valence band to the conduction band. And once you do that, you form what is known as the electron hole pair, which is a positive and a negative charge, a positive hole, a negative electron. And that distance between the two, which is an exciton, determines whether you have a quantum property. So if you have a size of a material that's equal or less than the size or the radius of the exciton, you have what is known as a quantum size effect. And that's shown in the next slide. So what's the quantum size effect or quantum confinement? So if you imagine a particle in a box model, so if you have a box, as you get the box smaller, and if you have electron in the box, you have a higher absorption. So as you make the box smaller, the absorption increases, and that's shown on one of the graphs here. And so these quantum dots, as we call them, have quantum confinement properties. And how does the properties manifest itself? It manifests itself in the absorption and emission band gap, and you can measure that using UV spectra or photoluminescence. So you can vary the emission. So what does that mean? It means you can vary the amount of light that you are emitting from the particle. And then you can see there on the slide the different colors of the materials or the particles, and purely based on their size. So a 2.3 nanometer will have a certain color, a 5.5 will have a certain color, and you can vary the size and the property. And as shown here, this is from the Bowendi group in MIT. This is the material they made, cadmium selenide, showing you different colors based on size. Now, so how would this be? So this property, where would it be applicable in technology? So here you see, if you go shopping and you want to buy an expensive TV, you will see that the most advanced TVs are the quantum dot LEDs. So they are made of quantum dots, which give you a very bright color and used in the display market. Another application of this property is in biolabeling. You can create biomolecules, and you can track the molecules in your body based on the emission. So they replace dyes. Another property of quantum dots or nanomaterials is the high surface to volume ratio. So you can imagine if you have a small particle, you have a larger number of atoms on the surface. As you increase the size of the particle, the surface atoms decrease, or the ratio of surface atoms to the size will decrease. So what will this be useful? It's mainly used in catalysis. So your surface becomes more important than the core itself. Okay, so those are the two main properties of quantum dots: the high surface to volume ratio and the quantum size effect. So general applications of nanomaterials, varieties. It's all out there in the scientific world, in use in catalysis, water remediation, water treatment, gas absorption. Solar cells are made of nanomaterials of quantum dots. LEDs, which are due to the optoelectronic properties. Photothermal therapy used in the body to treat cancer, because you have particles that emit energy that can kill cells. Sensors. So coming to our application. So Prof. Brown alluded to the fact of impact, and we are really changing the way we do research. And if you apply to NRF, you apply to all funding agencies, the first thing they ask you is, why are you doing the research? What problem are you solving? So you have to create a hypothesis. Previously, we did research based on exploration. We had an interest and we explored without knowing what the outcome would be. However, with public money, you have to solve a problem. So what problem can be solved? So in the last 5 years, we were looking at problems to solve. So one of the problems is the energy crisis. And obviously, there's a global concern for clean and renewable energy that can replace fossil fuels, sustainable energy. And one of the technologies that is identified as being important in this arena is the splitting of water, right? So if you imagine water H2O, if you split it, you'll get hydrogen and oxygen. However, it's an uphill reaction, as you would know, or you would find you need a catalyst. Okay. So the hydrogen that you get out of the splitting of water is identified as green, and I'll tell you why in the next slide. So green hydrogen is the big talk. It's the kind of buzzword or the flavor of the month. Many countries are investing in green hydrogen, including South Africa. We have a hydrogen strategy, and UNIZO is identified as one of the nodes or important players in the hydrogen economy, and I'll show you why. So there's a massive investment in hydrogen. So how is green hydrogen produced? Okay, so this slide shows you this kind of zero carbon effect of green hydrogen. So you create the initial energy, which you get from solar or wind or another form of renewable energy. You then add water, which can be salinized or desalinized water. The technology has moved in a way that you can even use salinized water. And you have a catalyst, electrocatalyst, that splits the water to form the hydrogen. What do you do with the hydrogen? You can store it as a paste, you can store it in a fuel cell, or you can convert it most likely to ammonia, and you can transport it as ammonia or another hydrocarbon. Right. So this is the future. This is what everybody wants to do. Now, the important point of the whole cycle there is the electrocatalyst. So this is why it's green, right? So you can, in your initial energy, it comes from solar, wind, hydro, ocean, geothermal. You have the electron that you're going to excite, and you have electrolyzer. Sorry. Now, within the electrolyzer is your electrocatalyst. The catalyst that everybody uses, it's the benchmark catalyst, is platinum. So unfortunately, platinum is very expensive. So the world is moving towards finding an alternative to platinum, or platinum with carbon or whatever. So that's where we are working in. We are working in trying to use other materials as electrocatalysts, which may not be as efficient as platinum, but there is always a trade-off. So you could find a cheaper material that may give you a lower performance, but you would still get your hydrogen. So what are the catalysts that the general community are working on? So two metals are quite popular. That's nickel and cobalt. So we've done a lot of work on nickel sulfide. We've tested our nickel sulfide. So there are other issues with the electrolyzer, the stability of the catalyst, the performance in acidic or alkaline media. So these are all issues that we have to tackle. The long-term stability. Does the catalyst degrade over time? Platinum works perfectly, right? But unfortunately, it's very expensive. So it's not very viable in terms of the economy, economically. So that's why there's a big race towards finding new catalysts. And if you do find a catalyst that's cheaper, works better or as good as platinum, well, you'll be very, very wealthy. Right, so how do we make the catalyst? So how do we work on the materials? So this is the general scheme for colloidal synthesis. What we do, we work on green synthesis, we work on solventless, and I'll give you examples of these: microwave, CVD, and spin coating. So these are the general methodologies to make nanomaterials in our lab. Okay. Where do we start? So we start with the precursor. So we have a starting material that will take us to the catalyst. So we work with molecules, or sorry, complexes, metal complexes from the periodic table, as I've said, as a kind of starting point. And then we can make films out of these precursors. We can make nanomaterials, and we can make nanocomposites. And so we have a patent on one of them. And overriding these issues, or the issues that we talk about, are using green solvents, shape control, phase purity, doping. So these are the important aspects that we work on. So it's important to keep, if you're working on something that's sustainable, then you should have sustainability running throughout the process. So we try to use green solvents, we try to use lower temperatures, lower energy, input energy, being lower. So we don't use high temperature processes. We use more moderate temperatures so that the overall process is sustainable. And obviously the end point is finding the application or testing the material. So where do we start? So we start with the colloidal routes. This is what we've always worked on from the time that we started the research. This is a one-part synthesis. So you take your precursor and you inject it into a surfactant, and it can be a long-chain amine, oleic acid, or a phosphine-based what you call surfactant, and you disperse it in the media, and then you then get your material out of it. So we mastered this process over time, and we have all the we know all the tricks and all the issues that are involved. Obviously, we want uniform size and shape. So we want to make a high quality material. The end point is always to have a material that's high quality. So what do we mean by high quality? It should have uniform size. It should have a phase pure. It should be, exclusive in one phase, and it should be scalable. So there's an example of a quantum dot, right? Made when I was a student in Imperial as a PhD student. So this is cadmium selenide. This is what won the Nobel Prize this year, right? Buwendi Group also made cadmium selenide, but we also worked in the same area. So this is a 5 nanometer quantum dot. It's probably about 3,000 to 4,000 atoms. The spots that you see, they are not the atoms, it's the reflection of the atoms on the HRTM. So this is an HRTM at Oxford University, which was a 400 keV machine, and it gives you almost perfect spherical quantum dot. And on the side of the dot, you can see on the left of the cartoon is the surfactant. So it's the surfactant that keeps the materials apart, and you have good dispersion. This is another quantum dot that we've made at UniZulu. These are lead sulfide, so giving you nice cubic shapes and rods, and so a mosaic structure. Okay, so very high quality lead sulfide, also made in competition with other groups. These are anisotropic materials. So this is bismuth sulfide, zinc selenide, antimony selenide, antimony sulfide, and you can see that they have different shapes and anisotropic properties. So all made at UniZulu. Now, there is a big trend towards making two-dimensional materials. So graphene is the kind of star material, but in competition with graphene are other materials that give you a kind of layered structures. So tin sulfide nanosheets are one. We have silver sulfide, which is unpublished work. So these are also made at UniZulu. Tin selenide, bismuth selenide. So these are the two-dimensional materials give you a higher surface area. They are more active in terms of catalysis, and they are regarded as the kind of future for nanomaterials. Now, so let's go back to where we start. So how do we make the material? So I spoke about precursor. So what is a precursor? Precursor is a starting point, a starting material. It's an organic complex that contains two or more of the elements that you want to make. So if you want to make a selenium-based or sulfur-based nanomaterial, you start with a thio or a selenium-based precursor. And different terminology. So you have what we call them single source precursors, single molecular precursors, or molecular precursors. Not to be confused with organometallic, which is a different class of material. So there's some examples of them, right? So this is our toolbox again. So these are the type of complexes that we want to work with. So they are phosphonate, carbamates, xanthates, ureas. So they are the different class. So this is purely inorganic chemistry. And what is the requirement for a single source precursor is that it should be pure. So we start off with a pure complex. So students will design and will make materials, complexes that are already published, or we'll make new ones, but they should be pure. They should be cost effective, scalable, so you need to make a lot of them. It should be stable, obviously not toxic or harmful to you, and you should have a known synthetic protocol. So that's a requirement of our starting material. Again, if we look at selenium-based, I'll speak about selenium because it's an interesting class of material. It's very difficult to make. So the classic or the reported starting materials are either diselenophosphonates, diselenocarbonates, and diselenophosphates or selenoethers. And the problem with them is you have phosphorus and then you have contamination of phosphorus. So once you make your end product, it's most likely contaminated with phosphorus. And there's also a toxicity problem, right? They have low air and moisture stability, and it's most likely will require a difficult synthetic method. This is an example of that. The Bowendi group, which was again the Nobel Prize winners, they use dimethyl cadmium, which is a very it's a metal alkyl, extremely volatile and extremely dangerous to work in the lab. So we are trying to avoid these kind of volatile, pyrophoric, and toxic precursors at high temperatures. So the original Bowendi paper, which is 1993, which won the Nobel Prize, that's the paper that won the prize, used all of these very highly toxic starting materials. We've tried to replace these materials with our precursors. And so a few years ago, we had a student from Pakistan, Malik Dilshad Khan, who will speak later, and he read most of our papers and was interested in working with the seleno complexes. And so there's a nice story on selenobenzoate complexes. So this is pure chemistry. I have to apologize if you're not a chemist, but just to give you an idea on the technology and the kind of advanced work that we do. So the selenobenzoate ligand was designed by him because we were working on selenium and reducing selenium using sodium borohydride. And we made this selenium salt of sodium borohydride. It's a very easy reaction. You can do that in the lab at room temperature. You take some selenium, put some reducing agent like sodium borohydride, and you will get hydrogen coming off. You can get a sound of hydrogen, but you ultimately get the sodium hydrogen selenide salt, right? And then you can take that and react it with a benzyl chloride, and then you form a selenobenzoate ligand, which is not very stable. And then you can take that ligand and react it with the metal chloride to form a selenobenzoate complex. So this was the first time that we made these complexes. So in addition to all what I showed you previously, the slide of showing you all the phosphine or phosphorus-based ligands, you now find a new ligand, a new complex. And this was the starting point for his PhD. So Malik did the work in around 2015, and it led to a host of high quality papers. So there's a setup. This is for so we took the metal. So we moved away from lead and cadmium because of the toxicity of lead and cadmium. We went into what is known as more earth abundant metals, and we tried to avoid lead and cadmium. So we actually went more green. So this is antimony selenide made by using the same ligand, and you can see on the right nice rods of antimony selenide. We characterize it using X-ray diffraction, which is in the department, and then we went ahead and made thin films out of the same complex. So what's a thin film? It's what we use a kind of homemade technology or using CVD, aerosol-assisted chemical vapor deposition. And you basically, I'll show you, and you can see on the right, you're getting rods or ribbons of antimony selenide on a glass substrate, and that's an SEM image of the material. So this is the setup in the lab. So you have a reactor, a furnace, two furnace, and a humidifier, and you put your precursor in the solvent of choice, and then you heat it up, and it gets transported to the furnace, and you have the reaction above the substrate, and you have deposition on the substrate. So this is a similar technique to normal CVD, but this is using a solvent. So you have a material, now you have a material on a substrate, which you can then do measurements on. So that is one area that we worked on. So the hot injection is our main route, and then we have the CVD route. And then again, I told you about the toolbox and the periodic table. So one of the nice ways of making new materials is actually joining them together. So you can take a selenium and a sulfur and you can form an alloy, and it's known as a solid solution. Obviously, there are some requirements and they are listed there. So they have to, they have to be of similar atomic radii, same crystal structure, and so forth. So this gave us a new way to form new materials, right? So adding two materials together. There are challenges because of low availability of precursors, reactivity. There's differentials in the reactivity. There's stoichiometric variation, reproducibility, and limited synthetic routes. So there's an example of that. So we took the antimony and sulfur and selenium, and we merged it, and we can then monitor the reaction using X-ray diffraction, and you see you have a nice variation, a kind of mixed material. So you have a mixture of sulfur, selenium, and antimony, and you can track that using X-ray diffraction. And that came out as a nice paper in the ACS journal, Applied Energy Materials, because we did the application of that material as well. So there's work that we went back to the phosphides. This is work done by Dr. Eric, who's here in Gaza, and he came from UKZN, and he was working on the dithiophosphonates. And what we found out there was that you could actually manipulate the your end product by changing the surfactant. So in this case, you could take a precursor. If you put it in trialkyl oxide or trialkyl, you form nickel phosphide. If you put it in hexadicylamine and in trialkyl, you form again nickel phosphide. However, if you put it in without the phosphine, like HDA and ODA or oxidation, you get nickel sulfide. So by varying the capping group, you change your end product. And this is quite cool because you can then make different materials under different conditions, right? And we did a whole lot of work on that and published the work in a high impact factor journal, where we said they were flexible precursors for either nickel sulfide or nickel phosphide. The phosphides are quite important, I think, in battery applications and in other areas. And we did test them for the water splitting, and I won't talk much about the actual results, but all I can show you that it did become a useful material for the application. Now, so another big area that we work on is not using the solvent. So I spoke about surfactants and solvents. Well, what if we don't have a solvent? What if we take the precursor and just heat it? So we just pyrolyze it in a tube furnace, and the end product is you get a material that's very clean, very phase pure, and it has much better properties than one with the capping surfactant. So this work was published again in a good journal, and it showed that the performance of the material was improved by using no surfactant. Okay, so it's a solvent-free synthesis, and you can make a lot of these materials because you could scale up, right, using the precursor. So I think this for industry, this might be the most viable technique, right? We use it a lot, and we've published a lot of work on this technique, right? So what does it mean? So you can take off the ligand either by ligand exchange or annealing, but that's expensive, laborious, and it may alter shape and stability. So it's better to not use a surfactant. So we go back to the precursor. So we can't use every precursor for the solvent-free synthesis. So one of our precursors that we identified was the xanthates. So the xanthates decompose at a much lower temperature than other precursors. So around 150 to 200 degrees, you can get material. So not a high temperature. And then it's shown by the Chugev mechanism, which is published. So this work was done by a PhD student, Janina, and she made nickel sulfide. It's a very highly cited paper. I think there's over 80 citations and published only within 5 years in Nature Scientific Reports, where we showed that you could make bare nickel sulfide with different phases And the nickel sulfide showed, and I'll show you, much higher performance than previously reported. So you see right at the bottom in red, you can see the high performance this is for specific capacity, in other words, using for energy storage. As a supercapacitor, it really has potential. So it has a 1287, and you can see the previous values are much lower than the material that we made. So that's why this paper is being cited quite highly. A simple technique to make an earth-abundant material like nickel, and also allowing scale up. Okay. So this route is very popular in our group. So Malik Dishar Khan did work on, initially this work was done at University of Manchester when he was a visiting student. And you can see we went ahead and we were interested in geologically and technologically important ternary materials. So we went from the binary to the ternary. So this is silver bismuth sulfide, copper indium, copper gallium, the whole range. You can, look at the periodic table, find a mineral that's found in nature and try and make it, right? And you never know that it may have a property that might be useful in energy, right? So this is our game. So this paper was published again in around 2018, where we made a whole host of ternary materials using the precursor, which was xanthates, and at lower temperatures. So these are our main papers on the solventless route, showing that it's quite well accepted within the scientific community, and it gets into very good journals because it's very simple and it's very scalable and practical for energy. So coming to my end of my talk, I think I don't know if Dr. Masakani is here. Okay, so I'll leave it to him, but this is our new toy, which is the 23 million Rand HR10, which Dr. Masakani is in charge of. And this will allow us to view materials on the nanoscale and also give us more insights into why materials behave in a certain way. And he'll show you all the functions of the machine. I would like to end by acknowledging my students. Remember, I spoke about everything which I did not do. These are the guys that did the work. I just have to supervise the study. And this is a great team and a very, very productive team and a very, very intelligent team. So on the left is Dr. Masakani, there's Dr. Khan, Dr. Ngwaza, students who are now submitting the PhD, Mr. Koza, Mr. Gift, and then Dr. Janina, who's gone back to Tanzania, Mr. Safundu, and Mr. Kumalo. And also have other students who have just started, Sean Francisco, who's a first-year PhD, Zimela, who's also submitting, and Dr. Malima, who's gone back to Tanzania. Again, some acknowledgements. This is Dr. Professor Ram Gupta at Pittsburgh State University. He does all our work on the application side, the electrochemistry. We are trying to set it up in our own lab so that we don't rely too much on outside collaborators, but he's been a great collaborator and we've done a lot of work together. And obviously the funding, especially University of Zululand, for allowing me the opportunity to work in this exciting area and to support me at all times. I know we always don't get along or we don't agree, but that's how it should be. We should always push each other and get the best out of each other. The DSI, SASO, Royal Society in the UK, and NRF. And I thank you for your attention.
Thank you very much. Can we get another big one?
Yeah, please.
Interestingly,
right. Thank you so much, Prof. River Prasad, for that presentation. At this point, it's going to be the Q&A, and Professor Fon. Oh, there's a video. Oh, it continues. Oh, sorry. How long is the video? Okay, no. How long is the video?
Okay. It's left to dry for a while. Let all the solvent is evaporated from the. So sorry, that was the initial one was the preparation of the grids. So now it's putting the salt, the sample on the grid. It's mounted onto the holder. It gets turned off. Now there's a kind of mapping that happens. There's a fine particle. You can go in closer. You can see the scale bar changing. So now you can see the lattice fringes. So you're going right down to the atomic level. So this is another mode. So we can do the crystallographic phase using the microscope. This is supplemented to the powder X-ray discussion. There is another phase, I'm not sure what it shows, but you can also do elemental mapping. So it can tell you how many, what elements are present in the sample. This is known as selective area electron diffraction, SAED. This is the STEM mode. So this is the element. So it's the dark field, so you can see the black background. See the different colors. The nice color.
You know, I always ask for another one. Can we give another one? Thank you very much. That was a fantastic one. Okay. Yeah, unfortunately, I came a little bit late, so I was hoping I'd come a bit earlier so that I can grind in with some questions. Unfortunately, there's no grinding here. I picked a couple of things when I came in, and the most important one was I saw a name called Ram Rupta, and he was involved with funding. So if we get the name of Gupta, you know, there's a lot of money. So if you want to get money on campus or join any research project where there's money, then I think you can join this team. I also picked out that the collaboration network with this project is quite huge, Prof. And that's really good. Congratulations to you and your team, and to the students that are sitting around as well. This is a great team to join if you want to travel for free. I can see you was talking about Manchester and so on and so forth here. So there's a whole lot there, and I saw that they were doing the solvent synthesis of nano. So also, if you want to join a team that is winning, a team that is going to be popular, I think everywhere now we are hearing about nano. So we are proud as UniZulu to have you on campus and to be selling our name right top there. So this is really good. I also saw quite a good number of publications out there and in highly rated journals. That means you are already flying the flag, and we'll continue to appreciate that. I would not like to start with questions, but I would like to listen from the audience if there are any questions for Prof. And then after that, I would ask my own questions. So I'll open the floor for questions. Do we have some questions for Prof? Interesting questions.
Well, I'd just like to pick up on what you said about the collaboration. So we started off a group that had collaboration, but what we've over the years tried to do was to show that we can do almost everything at UniZulu. So that was our main objective, and that's why we have the microscope, so that we don't rely too much on outside help. Initially, we did, we went all around getting our samples done, but slowly we've built up our own facilities, and that's what that was our aim. So hopefully, I've shown everything that I've shown you here was done at UniZulu. The work that was done outside was actually our ideas that were taken to another lab and done. So we've tried to be more independent, obviously still using our collaborators as our partners, especially with the application side. We are trying to set up our own electrochemistry lab where we'll be able to do our own, analysis on materials for their performance.
Okay, thank you very much for that, Prof. If I can pick up, I would think that now, instead of Prof going to seek other people, we will now have people from elsewhere coming to UniZulu.
Exactly.
Yes, can we give a big hand for that? Okay, can we have some questions for Prof? The floor.
Thank you very much, Prof. I think this is quite interesting. What you have done is very commendable. And as you have said, the University of Zulu is proud to have you around. And I hope you keep you more longer so that you continue flying the flag. When you manage to get the ship that you get, do you have a real way of manipulating it?
Okay.
And also assessing its property as to under certain condition whether it will change or evolve or change on its own. What control do you have after that?
That's a very good question, a great question. So the method we use slightly, you can make nanomaterials at different methods with different conditions. So initially when work started in this field, they use what is known as a colloidal route of solution-based route, where you're using room temperature and And in that case, in terms of the thermodynamics, if you can imagine at lower temperature, the shape is not very stable. So as you heat and you go to slightly higher temperature, it becomes thermodynamically stable. So it's very hard to manipulate the shape at a certain temperature, at a certain point where you stop the reaction. So the manipulation occurs through external factors, not through internal trying to. So whatever your final product, when you say you have a recipe, so you say I start at 200, I use this amount of starting material, so we have what we know as a recipe. So if you use that recipe, you will get this shape and this size. That's what we've been trying to optimize the shape and size. So once you get it, it's very hard to manipulate it from that point onwards because it's now thermodynamically stable. It is hard to then change that. And that's what you want. What we have a metric cobalt sulfide. In other words, instead of 1:1 ratio, there was a slight variation in the ratio. And we found that a slightly more metallic material might be a better performing material. Or if you have a dopant, it might increase the performance. So there are different ways of manipulating the performance of the material. So the impurity might actually be helpful in that case, or it may not.
Okay.
Yeah. Maybe that's the that you managed to through the check.
Very good question. We had a industry partner, or just associate who come along and find out what we're doing, and then we did send a sample of it. So I didn't show it, but the nickel sulfide system that's the best is Ni3S2. So it's a more metallic, right? And if you look at the literature, it's identified as the kind of Cinderella material for water splitting. So we did send about 5 grams of that to our partner, but he didn't come back yet. But we would like to test that on our electrolyzer to see how stable it is over a period of time. Does it degrade? Does it work in both acidic or alkaline? It could potentially be useful. But
Okay, we forgot to get your name and your department.
No, I'm outside. From
Okay.
yes. Kevin Dixon.
Thank you very much. I think we learn every day. I'm going to come to you in just. We learn every day, and I just had something called Cinderella material. I was hoping of Cinderella movie, and then I said Cinderella material. I don't know. Please, can you say more light on that?
well, that's
Oh, okay. They talk one day.
Yeah.
Oh, okay. Thank you. Over to you, sir.
Thank you, Prof. Well, I was wondering, Cinderella material doesn't turn back into a pumpkin at 12. I just have a question about
Do you understand this?
Oh, thank you.
Well, my question is more around your comment just now about saying, trying to call it, example of your adjustment and that come back. Where does intellectual property sit in this realm? Because clearly you went to an adventure and frontiers all the time, and probably making new discoveries on a daily, if not a weekly basis. How do you
well, I mean that sort of let's say that because Ni3S2 is known, but we didn't tell them, we just confirm. But we know how we made it, what we made. So if it was if you bought the form that you wanted to repeat that, you wouldn't know. You wouldn't know. Yeah, but it is, I mean, obviously something. Yeah, you have to have a MOU, and we have to go into kind of licensing material.
So indirectly, we're saying that you gave them coded information.
Yeah.
Thank you very much.
Thank you so much. My name is Tatalene from Young Research. So I'd like to compliment Prof and the team for the wonderful work and for putting up students that well done. I've seen that on the electronic report. From our students. So how are these techniques compared to
I mean, I think if what we found, and talking with other members of the industry as well, if you make something that's very useful to the international community, and you will have to characterize it, quality control. So it's used as one of the techniques for quality control to give people an accurate idea of what's in the sample to the side. But more importantly for us as researchers, it gives us an idea of what what is happening at the nano level and the micro scale to see how performance is linked to property. So that's our main task, is to see what is giving the performance and how can we improve it. So we have to go back to the to the basics to study the fine structure.
Maybe just a follow-up, maybe. We will take time on that a bit just to share with Yanza how the research work, the work that Yanza is doing, Yanza Metal is doing. Just what a little bit on that.
Sure. Okay, yeah, I mean, as a materials manufacturer, you would need information on your material, and we'll be able to provide that. X-ray diffraction, XRF would be one technique or two techniques, but you could go further, and what we've shown here, you can go into the elemental mapping and the particle size, particle distribution, and I think that we find that people want to know about it, and so your quality will improve, and then your price will go. So you get different variations in quality. So ultimately, you want to produce a material that's a high quality, so you're high price. So we're working with the Illumina guys. So they've been making 50 nanometer aluminum particle, right? So, but they want to go sub 50. So they need the microscope to show that. By who are in battery industry in Australia, they require the spec sheets to show the actual size. So I'm sure in your industry as well.
Yeah.
Size is important.
Yeah, so it's very important.
Do we have another hand?
I'm afraid of the last one.
No, there are more.
If there are more, I would like to do the last one because I think mine is not going to be touching directly on what Prof by the future. So I will allow everybody else to ask the last one.
This Prof. Okay.
It's based on the about, but what I wanted to know, you mentioned a couple of circumstantial, but isn't that narrow or it's specific?
Very broad. We work on, I didn't tell you, but we can make almost anything we want in our lab. Because the starting material is a precursor, and we can make, or we can use other methods. But in the country, nobody can touch us in terms of the variation. I mean, if you look at all our publications, you'll see goes from oxides to sulfides, selenides, phosphides. I mean, Dr. Eric is here, he's in the lab. You can ask him what we can make and what we can't. But there's nothing that we can't make. Metals, we've done work on gold, platinum, palladium, cobalt. It just depends on the application. So we try to narrow our focus because we want to specialize, so we chose hydrogen as our, but we're also going to go to carbon dioxide reduction, then two-dimensional materials, so it gives you a big window. And it depends on where, like, what's the hot material. So we're now working mainly on two-dimensional, looking at application side. So looking at CO2 reduction. So one material that we've made recently, bismuthine, so it's a graphene, is this bismuth, but on a two-dimensional sheet, and it gives you very good property for CO2 reduction.
Okay, Prof, that's quite interesting, right? To maybe some of us, this nanoparticle thing is very popular in a way that one is wondering how one can unpack it in a way that the layman can really understand what are the uses of these particles, because we've been getting nano every fee we talk about nano. So sometimes it get a little bit confusing. And can you, so I was looking, you talk about contamination, also not contamination, the organic component and the inorganic component of those materials. Can you share more light?
Yeah, so the organic component has a role in that it keeps the particles apart, right? But what we found is that for application side, you actually don't want them apart. You want them quite close to each other. So you take the organic group out, we have a solventless group, and we find that the performance for water splitting is much better without the organic part. But for biological application in the body, you would need the organic part. Because say if you're working with a metal, even gold or cadmium, you don't want the organic part, the shell, to be removed, because that would become toxic. So you need it to protect the core, which is your particle, from toxicity.
Oh, thank you very much for sharing more light into that. And I think there was some comment about patent as well. Yeah. Yes, sir.
Thank you. My name is Slibusit Nan. And thank you, Prof, for such an insightful presentation. You did touch a little bit on intervention being directed at green hydrogen. From a value chain perspective, I'm trying to zoom into a layman's type of understanding of what exactly intervention is. What exactly is the product that's intended for the market? Where are we trying to intervene? I know that the hydrogen economy is a developing industry for South Africa, and perhaps also globally. There's a lot of gaps in the market, and cost is the biggest driver of adoption of the technology. Green hydrogen, I believe, it's one of the most expensive. And how is this technology? What is the product first? And how is it actually hoping that we get something out? How does it actually fit into the value chain? What exactly are we trying to, where are we trying to intervene, and what exactly problem that currently exists that industry is looking for that you are actually making an intervention on? And maybe you can pack that question first as from a layman's perspective, what is the product? And secondly, being working with such a diverse group, and also there's international collaborations, IP becomes the most critical aspect. And how do you manage that in your publications and also in your engagements with other partners outside in terms of ownership arrangements?
Thank you. So your first question about the green hydrogen economy in South Africa. So, South Africa is a big producer of platinum and PGM. So, and a lot of the research is funded by the PGM. Obviously, they want to beneficiate platinum. So, in terms of, on the commercial side, there isn't much interest in trying to find a replacement to platinum. But as a researcher and as part of the international community, there is, I can tell you, a big drive to find replacements to platinum. So from South Africa's point, obviously, we don't want, platinum to be, but we also have the other metals, cobalt. Cobalt is regarded as, again, important material for applications. You can see the DRC, you hear stories where a whole hill of cobalt has been, which contains cobalt, been taken away by the Chinese. So the Chinese are very interested in cobalt. And you see the price of cobalt going up. It's a good metal to invest in. So in terms of the, from the economical and all of that, I don't know, there will be, I think, a basket of materials that will be used at different points for green hydrogen. But it has to move away from that, or at least not rely so much. So there's a limited amount of platinum as well. So anything that we find, as much as we're trying to solve the problem, we're also creating problems because we need the resources. So it is a balance, that's why we have, other types of materials that are, another one is metal organic framework. That's another, area that people are trying to, So I think for South Africa, we're still in a good position because we have earth abundant metals and we also have platinum and palladium. So, it would probably be a win-win in terms of hydrogen, obviously to get the cost down and to get the efficiency up. And storage is a big problem for hydrogen. How do you store the hydrogen? And so the whole logistics, in terms of transporting is, so these are the main issues in terms of hydrogen. So that's why Richards Bay is regarded as a hub because of being able to export it out of strategy. The day that the channel between Durban and Richards Bay, Rustenburg in Johannesburg, the mining part and so forth. The second question was about the IP. Yeah, so the IP, yeah, the good question. I mean, the funding is mainly from government, so the IP belongs to the university, as far as we know. In terms of collaboration, we have MOUs with collaborators. So thus far, we've had no issues with IP, but obviously we'll have to review it when we go further into the application side.
That's a follow-up.
Yeah.
I mean, I appreciated the video.
Yeah.
For anyone skilled in the art, is it not easy to copy from here and get to follow the steps here and fine-tune some of the things and be able to mimic or actually do exactly what it did?
Okay, for the HR10?
I mean, if you put a video that has a sequence in the process and program that you are doing, how much of that is IP related that could actually be easily copied by someone who's skilled in the same art as you? How do you manage disclosures in the video itself?
No, the video is just a standard procedure for using the microscope. There's no IP related to that.
Okay, one last question because we're running out of time. Prof. Unati.
Okay. Prof, I wanted everybody to talk the industry, the mine, and whatnot, so that
The name and the department.
Oh, my name is Munati Kolani. I'm from Consumer Sciences. So I think that now is leading to the kitchen. Because I think one mentioned that nanotechnology is one of those technologies that are really making a big mark. So I wanted to find out now, since we talk sustainability, and when we are making our innovations in the food industry and we are talking food systems, is there a role where you see that maybe, especially things like the packaging, we can actually maybe work together in because thinking about myself and Prof. Sarane, that I think now one of our biggest challenges to retain the indigenous component is now to a package that is going to be extending the shelf life.
Yes, I mean, the one important property which we've always wanted to explore is the thermoelectric properties of some of our materials, and that would be related to packaging and retaining, the temperature and so forth. Yeah. So it's a good point. Yeah.
Okay, thank you, Lord. When she said I'm from consumer science, I was like, God, please don't put this thing in my food.
Yeah, but maybe just a follow-up. Maybe just to pick up on the question, how far are we, where are we in that space in terms of, because I think even if you look beyond the Zulu space and consumer science, I think packaging is a big question more broadly. And I think maybe it could also fit into what Mr. Manana was asking, but not necessarily hydrogen, but to say, how could we tap into that? Is there need for this kind of a packaging, and then what is the dynamics like out there, in terms of demands for us, for broadly?
Yeah, I think there is, I mean, again, our job is, making the material and then studying the properties. And once we have the property, then trying to apply that property. So within the whole chain, the application is right at the end. But we have to understand the pathway to it. But again, it's a picking problem that we want to solve. So if we pick that problem, then we can try and, work through it and know what's out in the literature, what is already out there and how we can improve on it. I remember a few years ago, a good example, the platinum industry didn't know what, what extra uses for platinum in the country. And they call all, the big professors and, to a workshop and to find out how can we find new uses for platinum. And there were two main applications that came out. One was platinum jewelry, which became popular and is still popular. And the other one was using it to stop the as a catalyst for the for bananas not going rotten. So apparently it's a big industry that fruit goes goes off. But then men try to use platinum to to save the bananas. So, yeah.
Okay, colleagues, I think we are running out of time. I'll definitely talk to my wife about nanotechnology today. I'm not sure if she will understand, but thank you very much for the wonderful and informative presentation. And let's give a big one again.
Yes. Yeah. Thank you so much. We decided to be innovative, because there is no state there, so we decided to be innovative about it. So I wish to thank Professor Paul for this for facilitating this previous session. Thank you so much, Dr. Paul. You do things so beautifully. We most appreciate that one. Thank you so much, Paul. And I also want to thank Professor Rico Prasadu for the wonderful presentation. I don't understand nanotechnology myself, but I think it's simplified some of the things, so there is a takeaway for me from that presentation. Thank you so much, Prof. Right, just some quick announcements before we move to the next stage in our program, colleagues and students. Right. In terms of the exhibitions, the viewing of the exhibits, right? When you walk out of this door to your left, there's the Department of Consumer Sciences, right? And then to your right, there's the Department of Agriculture, as well as Creative Arts to your right. And then that's that. And then in terms of the food stations, all postgraduate students, will you be kind enough as to walk out through this way? There is food for you over here. And then for all our guests and staff members, you just walk out to your left, and then there will be food there when we get to the point of actually having our food. Right, so I thought I need to clarify that one. Colleagues, at this stage, therefore, we're going to proceed to the viewing of exhibits and refreshments. My understanding, therefore, is that it is in the process of viewing the exhibit that we also get to eat. Right, am I right? All right. And then before we move, I think Prof. Brown would need he wants me to present the token of appreciation to Prof. Prasadu, but I will still request and insist that Prof. Brown does that. He hands over to Prof. Prasadu. Professors, you can come this side. Thank you.
Yes. maybe that's also, thank you very much for wonderful engagement and as yours. Oh, you. Go this way. So we need to shake hand like this.
Nanotechnology.
And there's also going to be another section after the plenary, where we take photos and hand over. So they'll be that.
Absolutely. I think you heard what Prof. Brown said. After the plenary, we're going to have another session. So my understanding therefore, colleagues, is that at the same time that we're going to view the exhibits, that's the same time as well that we get to, have our food. Because viewing of exhibits and refreshments. Shall we do that, colleagues? I repeat, our guests and staff members walk to left, and then there's food. All our postgraduate students will be kind enough. The food is over here. Thank you so much, colleagues. I'll see you after the viewing for another plenary. Thank you so much.
That's very wonderful. We have a big run on that. Oh, that's it. Yeah, very
Going to stay then until so probably 2011. Then there's been other developments since then. You started building products, testing the machines. Started the production.
Oh, Shakti knew.
Nice to meet you. As long as we want everyone. Yes, they do. What I'm saying, after next week, they have responses from them so that they can look at or they can give us feedback on what they have taken from the program. So these are the beginning to sponsor on the program. You know, they just say, they cancel the training. After the training, yes, this is a good chapter from one of the students from the other school. So now this paper so all of them. These are published for the this one then are subject for the chapter and then so these are
We can clarify and James.
I'm supposed to, but I write it down.
Mr. Matthew is here. So it's good. In fact, with showing people in the thing. Also, another thing.
No, but that. All right, okay. April, when I'm more in that slide, no, that. Slide. Yeah. Right, but you need to. Is. Right. Okay. One. Office of project. Let's see. More in, my brother. Yeah, I'm good with that. I mean, I mean, the road. Just look at the photo. Now what about it? When I
Yes, like, looking at you.
No, Amaranta. No, hallelujah. Just behave, guys. Representing, yeah, I like that.
Yeah.
Great. Thank you for this one. What who's listening to our brothers? Right.
The family to pay for this hydrological. When the GIS platform, we integration this is question or rainfall map. This one is the temperature map. Value one
Afterwards, because it's in representing now. I'd rather eat afterwards. Oh, okay. And so we will have presentations.
Do you have your own presentation?
Yeah.
Can we save it in a USB?
Yeah. Let me use now.
Hello.
You know how flat.
So I think yeah. Yes. Thank you so much. Well, the three like it's like your head. Which one is your head? I don't see head.
And then, yes.
Siyadlala ukuzokuzanela ubaba ufuna ukanda laba bazosebenza because nanku usangene ngale ngingalenkinga yilo.
When I left my umbrella in the car, my raincoat in the car. Shelf life. And it's compared to me. I have but we expected to wow.
Okay, jawab back to the laptop. What do you have a presentation?
What's your challenge? How many slides are the presentation?
Okay, no, it's fine. I'll control them. I'll sit here. That's it. No, online.
Online. Okay, then it's
In fact, I wanted to check the member from someone. I think I checked that. Was this morning was working?
It's okay, I understood you. It's only that I think it was. I understood your question from the end. As the pilot scale. Looks like the products that I explained. So much discussion was put on.
So like every day,
I was wondering if we could just reconvene, colleagues. I'll look time is against us. Right, while we are waiting for everybody to be here, the moderator for this next session is Professor Kolanisi. Prof. Kolanisi is here. And then I want to quickly check if we do have the panelists. Professor Magarova, and here. Sposiso, Manana, are they here? Yeah. Oh, all right, okay. All right. And then Rosa here. Dr. Malik online, and Mr. Mike Chepikot, you here. So I want to say, once again, colleagues, I want to say for the second time, good afternoon, and we are happy to reconvene so that we can continue with our program. At this stage, therefore, I'm going to hand over to Professor Kolanisi who is going to be the moderator for this session of our program. Prof. Kolamisi, over to you.
Thank you so much. Good morning, Sanibonani, Dumelang. All right, my name is Unati Kolamisi. I'm a professor in consumer sciences. I am from the Faculty of Science, Agriculture and Engineering. You are so welcome. We thank the Office of Professor Brown for organizing this wonderful and insightful event, which is, I think, is the trendsetter, because I think, Prof, you have hit it on the nail. Thank you so much. Without wasting time, I am going to be inviting the panelists to join us here on stage, because these chairs are actually for you. Professor Evelyn Magoroba, please come up. And Mr. Musito Manana, greetings, Dr. Khan, and then Mr. Mike Chetty, also please come through, as well as Dr. Kevin Hendricks, please. All right, Dr. Khan, can you hear us? Hello?
Yes, I can hear you.
Thanks,
Yes.
excellent. Well, so much. Thank you so much.
Thank you.
I think that if you just keep your video on.
Yeah, yes, I can. Thank you.
All right. Ladies and gentlemen, before I can even introduce the theme for this particular discussion, I know that some of our panelists have prepared some presentation. I am just going to be giving you a rule that your presentation should not be more than 10 minutes. So I am going to be very strict. But to the audience also, when you are listening to our panelists, please take questions, notes, as well as on the online. Can you please write on the chat anything, your comment or a question or anything that and then the way in which we are going to do it, panelists, is that I'm going to give you an opportunity to present all of you, so that then later on we can have an open discussion, because I was told that we need to make this engaging. It's not about talking, but we need to share information and also maybe come up with resolutions. So if that is acceptable to you, I'll give you, I'll introduce you, and then you will present your presentation. After we've done that, we are going to introduce the next presenter, and then we do that. Is that okay? All right, thank you so much. Thank you so much. Ladies and gentlemen, this particular theme is actually talking about something that Prof. Brown mentioned earlier on in his speech. He said, it is through engagement beyond the university where we can make societal impact. I think Prof. Nourish also, when he was presenting, he did mention that even when you are applying for NRF, there is that component that requires you to actually explain how does this going to be making an impact on communities or bringing some kind of change or transformation. So I think this theme was actually inspired by that very same thought, when now we say from lab to the market, promoting commercialization of academic research. The time where the research products or outputs were only meant for the library are gone. The time where the research was only meant for the academic community are gone. Now, what is required is for us to say, what you have identified as a problem, what solution are you bringing on the table? Because we are talking about the agenda AU 2063, that is the African Union agenda, which have 7 aspirations. What contribution are we actually making as the University of Zululand with our partners in order to change the status quo? We talk about the sustainable developmental goals, just under 10 years, before we can now be held accountable about what we've done as a country as well as the global world, we need to be looking at research as well as innovation to solve those problems. It cannot be business as usual. I think we need to find some common ground where we can talk the same language and walk the talk so that we can be able to make sure that we move the innovation, we co-produce, we have that management system of knowledge and the innovation so that it is not only limited or restricted to the lab, but let us move now towards to the market in order to make sure that we are changing the status quo. Without saying too much, I am going to allow the panelists to actually unpack this theme through their presentations and some conversations that we're going to be having. So for now, I would like to introduce one of our first panelists, that is our very own Professor Evelyn Madoroba. Professor Madoroba is a professor of microbiology in the Department of Biochemistry and Microbiology at the University of Zululand. She holds a PhD in microbiology and MSc in biotechnology degree that she obtained with University Book Prize for Best Student in Class. Furthermore, Prof. Madoroba holds a master's in business leadership degree. She completed a postgraduate diploma in higher education and was awarded the Student Excellence Award for the module on diversity and the student in higher education. Professor is rated by National Research Foundation as a researcher in category C2. She is a recipient of the prestigious Fulbright Research Scholarship 2022-2023 program. She has extensive experience in the research and diagnosis of bacterial diseases that she obtained while working in industry as a project manager. Prof. Madoroba has supervised and co-supervised many MSc and PhD students from different universities in South Africa and has published 47 peer-reviewed articles with local and international collaborators. Prof. Madoroba is passionate about understanding antimicrobial resistance among bacterial pathogens and providing solutions to bioprospecting for new antimicrobial compounds produced by microorganisms that reside in extreme environments. She applies microbiology knowledge to upgrade the status of indigenous food through fermentation. Professor Madoroba is interested in microbial food safety, capacity building, skills development, and academic entrepreneurship. Prof. Madoroba, please take the stage and present to us. Over to you.
Thank you so much for the kind introduction. I'm going to talk to you about the theme that has already been talked about, but my emphasis as a microbiologist is that I'm going to talk about what microorganisms can do in order for them to have an impact. Since time immemorial, microorganisms have been taken advantage of and used to produce many fermented foods and food products. And then subsequently with time, different industries make use of microorganisms for different benefits. In this particular talk, I will give an overview of the role of microorganisms in biotechnology, where they can be harnessed to produce different products. And of course, I have a bias in upgrading the status of indigenous foods through fermentation, and I will go a little bit on that in the last slide. Microorganisms can be used for wastewater treatment. In this particular role, microorganisms can be isolated from different environments, and then they can be screened for their potential in terms of producing compounds that can actually be used to treat water. This alternative is more environmentally friendly compared to the use of chemicals. And for the purposes of taking research to the laboratory, what will be important is to bioprospect or to look for different microorganisms from different sources and then find out if they have the potential to be used for wastewater treatment. And more recently, with the advent of nanotechnology, there are what are called bio-nanomolecules that are being produced for the treatment of water by simply making use of microorganisms. Some microorganisms can produce what are referred to as primary metabolites as well as secondary metabolites. So taking advantage of the basic fundamental knowledge in microbiology, it is known that, for example, bacteria during their normal growth and metabolic processes, they actually produce metabolites for their own purpose in terms of growth, in terms of production of energy. But as people who are entrepreneurs, one would then try to take advantage of those primary metabolites and secondary metabolites that are produced by microorganisms for the benefit of human beings. A typical example would be the production of secondary metabolites. It is well known that there is a challenge of antimicrobial resistance, which is a global phenomenon. One can actually take advantage of microorganisms that grow in different environments, especially the so-called extreme environments, because they then produce metabolites with unique characteristics. And for those who are entrepreneurs, then they can bioprospect or look for different compounds produced by microorganisms from different environments and try to find out or prove the concept that a particular microorganism can actually produce a metabolite that could kill harmful or pathogenic microorganisms. And that scope is very wide. I'm just going to stop here because it is a lot to talk about that part, but it is important for those that are interested to try and then think outside the box, bioprospect, look for microorganisms that can actually have potential to be used for various purposes. These secondary metabolites, in addition to their role as antimicrobials, some of them can actually have anti-cancer effects and other benefits for human beings. And also, a lot of primary metabolites can be used, like for example, vitamins are known to be primary metabolites. And if one is thinking of trying to find out which microorganism can produce a particular vitamin, then they can bioprospect and then prove the concept, which could have potential to be taken to the market. In the pharmaceutical industry, likewise, microorganisms can also produce some compounds that have applications in the pharmaceutical industry. And in nanotechnology, I mentioned that microorganisms can also be used to develop nanoparticles that can be used for water treatment, which is more bio-friendly compared to the use of chemicals. So this is a general overview of the use of microorganisms, and I want to just dwell in shortly on the next slide, which talks about the application of microorganisms in sustainable agriculture. I think for those who were here yesterday, the issue of the role of agriculture was mentioned, and I cannot overemphasize it. So it is also important from a microbiologist point of view to think of how microorganisms can be applied in the agricultural sector. It is known that some microorganisms can produce chemicals that can be used as biofertilizers. Microorganisms also have an application in recycling nutrients, which is very important in agriculture. Some of them can produce compounds that can be used as biopesticides and are more environmentally friendly. Microorganisms can also be used for phosphate mobilization, and we have the so-called nitrogen-fixing bacteria, which are known to boost the production of different crops. So for those who are entrepreneurs, it would be good to always look out for these types of interesting microorganisms, prove a concept that maybe one has discovered this microorganism, it can be applied and it can yield better results compared to what is currently existing. And I now want to dwell on also on the role of microorganisms in the production of foods and beverages. It is the best diet. So microorganisms also have been taken advantage of. And usually these microorganisms are known to be able to transform raw materials to something that is completely different from the original raw material. They can improve the texture of the raw material. They can improve the taste of the raw material. They can even improve the nutritional value of the original raw material. And these microorganisms are diverse. They could be of a bacterial nature, and depending on the type of effect that they have on the food, they are categorized differently. We have, like, for example, lactic acid bacteria, which are personally biased to us because I am also producing a product that is made due to the effect of those lactic acid bacteria. I think for those who have been outside, you see my product. So I've used those microorganisms personally for fermentation. You can see those tomatoes, they are not from the internet, and it's actually the way that I'm doing. So I have taken advantage of the benefits of sorghum, which is known to be drought resistant and has a potential for future in Africa. So then I've taken advantage of microorganisms, used them for fermentation to produce products that are actually almost ready to go to the market. We're in the process of trying to find out what consumers think about the products that we're making. But there is a huge scope for those who are interested in developing products that are similar from microorganisms. One just needs to check their safety, and they can go to different environments and try and isolate these microorganisms, test out their potentials, prove the concept, and then develop a product which can actually subsequently be put on the market. And you can see from the other picture of those that is not from my work, but it is the use of microorganisms that is out in the production of cheese. There is a particular type of microorganism that can actually lead to the formation of those eyes in the system. It's propionic bacteria that actually do that process. So microorganisms can be harvested and taken advantage of by human beings to produce many things that can be taken to market for the benefit of human beings. With this, I want to take advantage and thank everyone who's there for the opportunity and to share what I love most about the role of microorganisms for the benefit of human beings. Thank you so much.
I think some of us never really thought about the good bacteria or microorganisms. Now we know that the future looks brighter because microorganisms can also contribute not only to our health, but or well-being, but also an entrepreneurship and livelihood opportunity. I think when we are thinking about from lab to the market, the questions and the comments that now you are actually posing to us is about now give us stages to say, isolate, proof, concept, take it to the market. So I think these are the things that we need to look into and then ask ourselves, how can we seize this opportunity? And also look at the University of Zululand, the positioning. How can we actually change the status quo of the local communities by using these microorganisms? Because it's not only the food. Water is one food component that we always forget, and water is life. So I think we have an opportunity. Thank you so much, Prof. And please do write your comments and questions for later. Now I am going to be introducing to you Mr. Sbusiso Manana, who currently holds a position of the head agriculture in the business unit and a strategic technology sector at the Technology Innovation Agency. We know it as TIA. Mr. Manana is a chemical engineer, holds an MBA qualification. He has 13 years of work experience within the technology and innovation development, 7 of which he has served here as both as business support service manager and commercialization manager in the agriculture business unit. Prior to working at TIA, he worked in small and medium enterprise development sector for 10 years as an industrial advisor, operations manager, and a branch manager at Small Enterprise Development Agency and the KZN Manufacturing Advisory Center. His work experience in the corporate sector includes having worked for the General Motor Corporation, Idwaba Carbonates, Mondi Paper, and Anglo-American Corporation. Mr. Manana has also served in a number of directorship positions, which including also have served as the president and chairperson of South Coast Chamber of Commerce. Mr. Manana is also known as one of the advocates for social and youth innovation, rural development, SMME development, as well as transformation, having served on a number of forums driving interventions in the areas of radical economic transformation and inclusive economic development. Mr. Manana, please take the stage.
Thank you. Thank you, Prof. And once again, I have great everyone, especially academia, the students, as well as industry that is underrepresented the country here today. I think I've exhausted my airtime. I said quite a mouthful yesterday in the address. All that I will be doing today is just to fill in the gaps on the information perhaps that I would have loved to share with you yesterday. I'm quite a journeyman. I'm well traveled, of course, across the different industries, having worked in the mining sector, in the motor industry, the service sector, and here I am, I'm in the financial sector, only being a chemical engineer. And that says to me, there is quite a lot from a developmental perspective that we have to look at. From what I'm going to share with you, looking at how we look at problems as opportunities, saying from lab to the market. In positioning the university work, one would always ask a question: how does the university respond to challenges that globally affects the world, but also closer to home that affects the communities? One example of currently what is happening in the global space of instability, the fighting of Ukraine, Russia, Israel, and many other pockets of instability. How do we view that? It's instability, yes. It's got human element that we always kind for. But in that situation, the problems that arise, one amongst many is, if we look at the Russia and Ukraine situation and how it impacts South Africa, from a globalization supply chain problem, we've got a lot of dependency from the food supply side that is impacted by this instability. The fertilizer has shot up, and it's also a reason of supply. So it means the supply has dropped because of the global supply chains disruptions. the wheat supply has gone down. The maize supply, even to Africa, by just looking at this one super arrangement, which is resulting in this instability. Africa as a whole is food threatened. So what does that mean? It means in terms of the opportunity it presents is South Africa must develop its own sustainability means. So we need to go back to the drawing board. Whatever we are not able to produce there, we need to find innovative or researched ways of how do we adapt whatever crops or whatever products so that we can actually plant them and produce them in Africa. If we had not had before a good wheat variety that the industry, which is producers, are not happy with, because there's a reason why we are importing when we have some level of supply even locally. It's because maybe there are certain specs that we're not meeting with our own internal production, and hence the option to go out and actually get wheat from outside, which the products that the consumer is looking for is meeting. So it means from a production perspective, genetically we have to find ways and means of putting together some protocols from a science basis that helps us to produce this in the manner that enables that we meet the specifications of the processor of food. The next level is, if we are food insecure, we have to sit back and use our lens to say, what is it that is the depth in the market and which commodities we are short of, and then we open up our capabilities to explore those markets. And research is at the forefront. Research is at the forefront. In some instances, we might have to actually connect with other partners outside of our borders to get the seed material, and actually exploring how to produce and get to the level of, those superior varieties, of course, superior performing varieties, and actually adapt them to our local conditions. So science is at the back of how to, so that the farmers don't have to struggle. The farmers won't actually take any seed that is underperforming. They want seed that has been tested, researched, and there is enough data to prove the yields that are superior, and also it meets the quality and specifications that the market has set for itself. On the back end of what our local capability is in terms of responding to what our biodiversity provides, I'm happy that today I was able to do the walkabout to see that there are products that are being agro-processed, which is one of the interventions that from the agricultural big question of food waste, which says more than 40% of food produced from primary to plates is lost along the value chain. From when you actually put the potato down, and then you are actually harvesting. Some of it is chopped off, some of it is just damaged. You can't even put it on the market. Already it's wastage. At the level of the market, it stays there for a few days, it loses its quality, it's wasted. At the production, at the processing phase, there's a lot of fields that are thrown away, which could be converted to good products that are edible or can have other functions and use. But we need to explore what those are. Right up until the end, when it's on the plate and then it's actually discarded. We still can use that. There is already a initiative of nutrient recycling. I saw something that I spoke to that. Nutrient recycling, where there is a project that looks at how do we use wasted food to produce new protein source through fly farming. That's what is coming up, and it's actually taking off very well. We actually supported an initiative, which we essentially scaled it from the lab into a 100-ton production facility. It's in Cape Town, nutrient recycling using fly farm. So basically, the big question and the gaps that exist all over in our area of operation needs answers. It needs us to respond through science so that we can innovate or research new products and services to plug the gaps. So the issue of food waste is a non-starter. It happens from right at the beginning, right to the end, when food is actually produced and thrown into the bin. And we don't have a good code of reduction of that food waste across all type of foods. Even there, you look at livestock production, it's the same. So we need to find ways and means of productizing waste to benefit the economy. And the other element I wanted to touch on is from the introduction earlier on in the morning, which sought to actually give us a glimpse of what future the technologies hold for us. That nanotechnology for me, if I position it at the back of my mind, is a platform technology. Meaning it is not, its application is quite broad and vast. We still need to explore what other areas the technology can extend to. From a model of quadruple helix of innovation, we always need to place two things at the front when we do research or when we innovate. Mainly it's the market, and the market supplies society. When we do research, it's the market, and the market supplies society. But where do we get the money to fund the risk? It's government. In packaging whatever program or initiative that you are thinking is going to hit the ground running, if it falls outside of the policy of government and priorities, I think you may actually find a struggle to deploy that. Because before we even fund any technology, we say, where does it rank in the priorities of government? What problem does it solve in the main? Is it solving an issue of food security for us? Is it solving an issue of energy crisis for us? Is it solving an issue of water crisis? If it does not tick any of those, and another element comes just after you have answered those questions nicely, what about transformation? We've got a ticking time bomb of high youth unemployment. If all our work does not respond to opportunities that are creating chances for youth to enterprise, to entrepreneurship opportunity and starting their own companies, we may as well actually shut shop. That future for them on the economy, it means it's dead. So when we package and look at all these initiatives, let us look at what opportunities, what impact are we driving in terms of transformation, and youth being at the forefront. And our coming from an agricultural background where I am working mostly with the agricultural sector practitioners, Most of them are old. And when you try to suss out what the problem is, it's because the youth also is not interested. Agriculture is very difficult. So how do we make agriculture or position it for the youth to have an interest? It means we have to work twice as hard to make agriculture not what it was before, so that the youth can actually begin to appreciate opportunities that the agriculture presents for them. Urbanization, or actually modernizing agriculture, is at the forefront, meaning we have to double our efforts to present agri-tech solutions. And those are opportunities that we need to position for the youth. And produce food where people are in urbanized settings, meaning we have to change the landscape of agriculture. But always it's funding. I said, if funding is what is the big problem for innovation and research, it must respond to government priorities. So from our theme today of left to market, I would like maybe to just flag those couple of themes to say, in our efforts, that is from a university perspective, to try and drive new innovative products and solutions, the market should actually remain at the forefront, and our society is, but government is critical, because if we are not responding to the challenges that are prioritized by government, it will be difficult to actually secure funding, especially at the risk component. And the risk phase is research. No one wants to fund research because it's prone to failure. That's the nature. And also, because we want to actually encourage good research initiatives, want to fund, but the response must be against the government priorities. It doesn't matter even if those priorities extend to our continent as a whole, but as long as the size of the problem, we can quantify and say how big the size of the problem is, then we are actually resolving. So be it. So be it. That's perhaps in the long and short what I wish to share as an addition to yesterday's contribution. Thank you.
Thank you so much. I think it was a mouthful, and actually, I think it was complementing what Prof. Madoroba said earlier on, because she was saying science matters, and now we are saying yes, science matters. Now, what we also need to do is to adopt a developmental perspective, because we cannot do anything that is not going to contribute in changing and bringing some kind of value into our society. And you have touched on so many aspects that when you were now trying to explain and present this developmental perspective, where you sort of give us the dynamics that are actually existing currently, globally as well as local. I think we are going to unpack them when we are engaging in our discussion. But what you also said, what is important now is when you are now thinking of this innovation as well as making this change, yes, it starts with research, which you say it is quite risky, and nobody really wants to take charge because it might not be giving us the answers that we want. But at the same time, we as the academic institutions, we need to align our agenda into the policies as well as the topical issues that are affecting the government. And then when we are actually now presenting our innovation as well as the technology and part of our research, we need to think about the market, about the society, so that we can be able to also say that is our contributions we have brought transformation. So thank you so much. I think it's just for you to also think broader, so that when we are engaging, we can be able now to unpack on these points more. So now I am going to be allowing Dr. Khan, who has joined us online, to come through. Dr. Khan, I don't have your biography with me, so if you can just please give us your biography before you can actually also contribute on from the lab to the market. Over to you, Doc.
Thank you. Let me just share my presentation. I hope you can see the presentation.
Yes, we have.
Okay, thank you. I am Dr. Malik Dilshad Khan. I work with Professor Niresh Prasadu on nanomaterials for energy technology. My main focus of research is to design and develop materials not only for energy generation but also for energy storage materials. I am initially from Pakistan, and I've done my PhD with Professor Niresh Prasadu, and then I've stayed with him for postdoc. And during this period, I also had the opportunity to visit different European countries to do the research. For example, in the University of Manchester, I stayed 1 year in the University of Manchester, and same in Poland during my PhD on the research of it. So I can say that I can combine the knowledge of 3 continents, Asia, Africa, and Europe together, come up with the solutions. So I really admire this step of bridging the gap between the academics and the universities, that we always feel that this is something that there is a, like not a proper connection, like from where we can take our materials from our lab to showcase to make them into first into prototypes and take out into the market. So universities, if you see in universities, one of the main important advantage of doing this is that they do both kind of research. Like we do one basic research which contributes to the basically fundamental knowledge and knowledge expansion, and then we also do the applied research, which is based on the target oriented, like based on the problems. So we identify the problems which are what are the global or national issues, and then we align and streamline our research according to those issues in order to respond to those, to make the solution of those problems. So I think that Prof. Prasadu has already explained that different range of materials which we use. So and we focus more entirely on the sustainability of the energy. So I'll just give you a few examples, like how we are streamlining our research with the main issues of the research and sustainability. So first of all, we identified like one of the this problem is not only a national issue but also at the global level. Like you'll see that the use of the fossil fuels, coal, gas, or petroleum, they are problematic to use. What are the problems? Number one, they are not sustainable, they are not renewable. Then, as the esteemed panel member also mentioned, that when there is a conflict in some region, so it can disturb the whole chain of supply. Then if you are not an oil or gas producing country, your economy can can be in turmoil because of this disruption in the supply chain and the price hikes and all these things. So that is one of the things, that they are not sustainable, they are not renewable. The second thing is the major problem they are causing is that they are causing to increase environmental pollution. And you'll find out that because of those carbonaceous particles and effluent gases by the use of these materials, there are a lot of health issues that are also rising in the general public as well. So now, in order to, if we move forward, there are like 2 ways of doing, moving forward. Like what we can do is we can either improve the already existing technology, or we can develop new procedures to do it. So I always tell my students that whenever there's a problem, actually it's like it's an opportunity for you to showcase your to showcase and implement your knowledge and skills to solve that challenge. So first of all, like if in order to replace those fossil fuels, hydrogen has been identified as one of the most potential material for as a fuel for the next generation technologies. So why hydrogen? Now hydrogen is a sustainable and renewable, and it's a very it gives you a clean energy. Why? Because when it burns in oxygen, so it combines to create water there. So there will be no basically zero carbon footprint by the use of this hydrogen. And then there is one important thing is that hydrogen, the starting material is very cheap and widely available all over the world, that is water. So if you are able to, what we simply do is take the water and split it into its constituents, that is hydrogen and oxygen. So that would be the best way to, gather hydrogen at a very cheap rate. But then there is a problem. Now, problem is that this water is a very thermodynamically stable molecule. If you see that even if you heat it at 100 degrees centigrade, it boils and converts into vapor, but it still stays water. So it is in vapor form, but it's in water. It's not like converted into hydrogen and oxygen. So in order to convert them, that there need to be a technology, like it's some sort of technology in which we can split the water into hydrogen and oxygen. And then this hydrogen, when this will be stored and used in industries or energy sort of applications, when it will give back water vapors. So now we need to identify this technology X. So two best forms of the most potential form of technologies which are globally identified are either electrocatalytic water splitting or photocatalytic water splitting. Now in one of the limitation again in this electrocatalytic or photocatalytic water splitting is that so far there are some catalysts which are required, which can catalyze the decomposition of hydrogen, catalyze the decomposition of water into hydrogen and oxygen. So far the best catalysts which are identified are either platinum or iridium based complexes, which are although luckily South Africa has a lot of deposits of platinum, but it's a very expensive metal. It's a very expensive metal, and it's not like available for to adopt the technology at a scalable level. So what we do is we design the suitable catalyst nanomaterials which can mimic the efficiency and stability according to up to the level of those noble metals. So same goes for the photocatalytic water splitting. In photocatalytic water splitting, we instead of electric, we usually use the sunlight. Again, we need some suitable catalysts and which can catalyze the decomposition of water into hydrogen and oxygen. So we in this regard, what we do is we are using we have already created, Professor Riva Prasad is doing nanotechnology from like 2000. So what we have done, prepared a lot of nanomaterials. Now what we are doing is we are categorically, rationally checking like which materials will be more comparable to the activity for the comparable to platinum. So next, same if I check, like there are another main issue which is rising right now, and it would be like you'll find out that there is a recent very boom in the use of electric vehicles, and there are like in Europe and all around the world, like they are promoting that, and they are trying to reduce the cars, electric vehicles, which run on the fossil fuels and convert it into the batteries. But when we check for the batteries, so far the best battery, which is so far the most efficient, is the lithium-ion battery. But again, there are issues concerning with the lithium. One is that it has like we need for electric vehicles to operate for through long distances and long charges, rechargeability. So we need materials with a bit higher energy density. So lithium it's a good material, but not up to that mark. Now, again, if we check the global availability of lithium, you'll find out that there are only 6 countries which have the almost maximum deposits of lithium. So again, it's an issue. Safety concerns that lithium is it's very reactive and explosive material. So again, that would be a concern if we use so much lithium in all the electric vehicles, that would be a problem. Then once the battery is finished, so again, recyclability and toxic residual issues. So in that regard, so at international level, the research is going on is to check the replacement of lithium-ion batteries. So they identified as metal air batteries. The metal air batteries, they find out that the best material is so far which can replace lithium-ion battery, the zinc air battery. So now in zinc air batteries, there is a problem that zinc air batteries, if you check, like it takes oxygen as a reactant, but it requires 2 reactions, oxygen reduction and oxygen evolution for rechargeability. So usually the catalyst only promote 1 reaction, like they are both in opposite reverse reaction. So what we have done in the past few in our papers publication, we have tried to create a bifunctional, multifunctional material which can promote both reactions, not only oxygen reduction but oxygen evolution reaction as well. So that is one of the focus of our researches as well. Like one of the PhD students is working on these materials to create the bifunctional catalyst, which can catalyze both kind of reactions and selectively, like when it is required, the reaction can go in that direction. So oxygen reduction reaction is a bit difficult and very interesting reaction as well. What is the reason is that it occurs in 2 steps. So oxygen can be reduced into hydrogen peroxide or into water. Like when in batteries, when we see the batteries, the preferable reaction for the batteries is that oxygen should be converted to water. So it is more energetic reaction. And it has its own advantages to avoid the corrosion of hydrogen peroxide. But there is another advantage of this reaction. If you tune the selectivity, if you are able to stop the reaction at the first step, like the conversion of oxygen into hydrogen peroxide, that is also a very important reaction because hydrogen peroxide is a material which has been used in so many different industries, cosmetics, agriculture, textile, and it is also used as a fuel in rocket industry, hydrogen peroxide, and different chemical synthesis. So this is one of the on the side. We just prepared one of the catalysts this year. This is one of the very recent work. Like we tune the activity to stop the reaction at either hydrogen peroxide or to reduce the oxygen to water. So third and last but not least is that one of the major problem, again, not only at national level but at global level, is the carbon dioxide, increase in carbon dioxide. Now, if you check like the anthropogenic activities, we have created so much the amount of carbon that it is causing severe damages to environment. Now, if you check this, this table, and you'll find out that if for every 500 gigaton of carbon, there is a rise of almost 1.5 degree in global warming. So if we continue the current trend in increasing the carbon amount, if it continues, it is predicted that by the end of this century, you might observe a global warming temperature in almost of 4 degrees, which is a very devastating for not only for us, but ecosystem and all the environment. So what we need to do is we need to decrease the this amount of carbon dioxide. Now, as I already mentioned, that there are technologies which are being developed in one we are developing technologies in which we avoid the use of materials which produce carbon. There is another way in which we should use carbon dioxide to convert them into useful materials. So there are researches which are going on in which carbon dioxide is being converted into useful chemical, which can be used in different chemical materials. Again, this carbon dioxide reduction requires, or conversion into different carbon-based materials requires different catalysts. So this is our real focus. We have identified a few materials, copper-based materials, which are promising, but we are doing research in this direction now, and hopefully we will come up with some good solution. So thank you. I hope I have not taken extra time. Sometimes I go beyond. Thank you.
Thank you so much. Thank you so much, Dr. Malik. I think that you have done an excellent job in giving us an example of now how the technology can actually benefit the communities, as well as talk into the topical agendas of the global world, because we all talk sustainability, reduction of greenhouse gas, as well as carbon dioxide. And I know that most of the researchers or innovators, when you also go and present your technology or innovation, these are the kind of questions that are being asked. And I like the way in which you have actually presented that slide that is actually telling us exactly how you reduce the carbon dioxide and all that. So thank you very much. Please keep on joining us. There might be questions later on and further engagements. I saw people scribbling down, so I think you will have lots of questions later on.
I'll be happy to respond.
All right, thank you so much. Thank you so much. I am now going to be introducing Mr. Mike Chetty. I'm going to start by saying a near end of career individual. I get the beard. Who is grateful for the manifold opportunities that have happened along his path to enjoy successful career of over 40 years. And he has spent the better part of 27 years of his career managing an applied research laboratory in the forest sciences. A specific focus on soil, plant, and wood fiber analysis. Institute for Commercial Forest Research, University of KwaZulu-Natal. In the recent years, 7 years, he has taken responsibility for the business development initiatives of his current employer, LECO Africa, within the KwaZulu-Natal region. I have read now the relevant achievements that we have. The one includes the CMS. I'm not sure what it stands for. Maybe you can just tell us: training and troubleshooting with LECO, specialist training in touch lens, study tours, because I think you, in these 40 years, you also enjoyed traveling. So maybe that is another trick that you need to just, because I think when you are an innovator, you also need to create an enabling environment for you to be productive. So please, Mr. Chetty, share with us, how did you do it? Because I like the successful. Can you please share with us?
Thank you, Madam Chair. If you don't mind, I would prefer to stand on the left-hand side here. But greetings and thank you to Prof. Byron and your VC for the invitation and the opportunity to chat to our friends here at Green Hill. And I would like to also extend my thanks to my colleagues and friends and associates that have accepted the invitation from industry. I see of note, Tonox is represented, Nyanza Light Metals is represented. Thank you very much. This part of my discussion relates to some level of navel gazing, casual chats with Prof. Riva Prasad, and subsequently took some form and shape with Dr. Byron for a bunch of months. And the basis of that talk was, how does one, we have access to a range of technologies. And my thinking was that there's a range of industries out here with unique technologies and offerings. And clearly, from my observation, the last 6 to 7 years that I've been traversing these paths, I get the feeling that there had to be a platform where we could use that as a vector to either demonstrate the technologies that are available, alternatively, for students and cohorts from the university, a safe environment to present some of their research work to the broader industry out here in Zululand and Richards Bay access. So that was essentially some of the conversations we had, and that has metamorphed into this discussion today. On the left-hand side. Yeah. So some of the discussions we've had, we would like to use this framework, or rather this opportunity to establish some level of industry representation together with academia. And I would see the way forward is, and I'm calling it loosely termed a technology transfer proposal or plan. Representatives from each side of the divide to sit together and perhaps plan forward a regular section of meeting. It could take the form of a once semester session to present specific topics of research evidence here. And once in a while, perhaps we could get some of the, and I'd use this word again selectively, non-proprietary technology that's in use here and around, Richards Bay, if I get any access. I mean, your university subscript says a node for applicant thought. And perhaps we could start developing on those nodes and establish sub-nodes within the environment to actively engage with the local industry and learn, really learn from both sides. An opportunity for PhDs and master students to present, defend their thesis, a platform for industry and academia to discuss technology gaps or mechanisms for example, in acquisition of specific technology. I mean, you've got Tronox down the road who are looking into various aspects of their processes. You've got Nyanza Metal that are starting up their operations here. We've got RBM down the road. We've got Monty, and all are using some form of analysis in their processes. Surely there's opportunity to either enrich or improve the efficiency of some of those processes, or look at alternatives. We've had lots of talk about green chemistry, certainly the buzzword, and certainly the activity going forward is opportunity. I mean, the Monty processes at the moment are pretty much ancient. The production of wood pulp from trees. I've had some level of insight into that in my previous life, and I'm absolutely sure there's opportunity there. I see hydrogen peroxide was mentioned in Dr. Malik's presentation. You know, not too long ago, sadly, you had a tragedy down the road, yes. It was NCT Forestry. Now, the genesis of NCT cooperative started way back in the late 80s, early 90s, where the farmers were growing the trees and the cooperative was the marketing or the niche organization. They contributed to my previous employer, Forestry Research, as a combined entity to provide better trees, to withstand current temperatures, to withstand drought, site-specific trees. Those piles of wood chips that we saw there, by current value was 3 billion each. Sadly, they lost, I think, 2 or 3. But that's the kind of nature and importance of each type of engagement, I believe, that the university can start up or initiate at least. And also comes with that patent and proprietary aspects in terms of technology patents. There's another thought. One must also balance that with what the Americans like to have these fancy terms, but I think it was Microsoft or IBM that spoke about blue sky technology back in the 80s. Blue sky technology is research rather. It also facilitates the university to move the frontiers of science forward. So yes, let's not, while we guided by the end users and the government funding, which should be directed to specific problems, let's also not forget blue sky technology also advances your frontiers of science, although small but incrementally forward. So those are the technologies, as Prof. Riva Prasad said, started off with the chalice that we all know from Dan Brown's book. And that was so many years ago. To today, nanotechnology is the forefront for delivery site-specific medication in your body, for delivering thermal-sensitive products, for example, food, refrigeration, etc. So let's not lose sight of that. Blue sky technology does have its place, but perhaps the proportion that we want to look at. And yeah, that's just some of my comments there. And perhaps, as I said, a business development person. Oh yes, and I had the opportunity and privilege to tour with Dr. Masikana about 2-3 weeks ago. Your wonderful facility there. I gathered from Dr. Riva Prasad's talk. Yeah. Plus minus 23 million or so. It's a massive investment. There's collateral. Let's use that to advance some of the areas of work there locally. That engagement with industry, that platform, let's use that as a vector to now justify the existence of this technology right here in Zululand. And from what I hear recently in the both business and economic times, apart from Durban, Richards Bay is the next growing high growth point for industry, and so let's take advantage of that. And maybe we'll steal the capital away from the But yeah, that's all a talk for another day. I just want to perhaps, as I said, business development officer, so I guess I need to have a little bit of a punch. But I want to talk about what LECO. LECO stands for, it's an acronym, Lab Equipment Company. What we've done in terms of partnering with university and partners of technology, both in Europe and locally here in South Africa, just to give some relevance as to how we fit into the bigger scheme of things. So LECO is a family-owned business from 1936, in existence for the better part of 80 years. And you'll see that that campus in Michigan is both your R&D center, your manufacturing centers, your customer experience center, global support center, from all of the same campus. So from concept to product, we often sponsor and support researchers across the world in centers of excellence, taking those advancements in science and converting them into potential instruments or changes in our current instrument to improve efficiency. Typically, example of some of the algorithms that are used in our chromatographs are taken out from some of the research done at various, I believe it's Fisher ratios that are used for looking at different types of changes in the chemistry of organic material. And now we've got software that's able to improve your workforce so that aspects that used to take hours on end of tedious calculation are now literally done within a snapshot. So that's some of the work that we've done. Typical collaborative efforts. I want to specifically mention University of Rostock in Europe. Here we have and I'll just refer to the original article. University of Rostock, interesting enough, I believe was established in 1814 and is approximately the oldest known university that I believe in Rostock. So together with the Helmholtz Institute, we have established a legal, what is known as under the stewardship of Prof. And the Germans use it, Dr. Ralph Zimmermann, a joint mass spectrometry center, which Dr. Zimmermann leads. It also serves as the chair for analytical chemistry at the University of Rostock, as the head of Comprehensive Molecular Analytics Corporation Group at the Helmholtz Center in Munich. some of the comments that we've made here, or I know here from the article, NICA was honored to support the work of Prof. Zimmerman and the Joint Mass Spectrometry Center, characterizing complex molecular mixtures. Said Jürgen Volt, that's a technical product specialist from Europe, at the European Life Center and Chemical Analysis. We are confident that his team will significantly benefit from the advantage provided by a high-resolution top mass spec. For the past 10 years, at the Helmholtz Center in Munich, we have worked very successfully with a GC top time-of-flight mass spectrometer. In the framework of our most recent cooperation, we are now very much looking forward to new exciting applications with the novel LECO fast resolution. That was the software that I was talking about on the LECO process. That's a typical example of where industry and can partner with high-tech companies and move the G's forward, for want of a better word. The snapshot in the middle is Prof. Titus Ngani at Genisa, who recently installed a hybrid TGA unit. And I'll just go through the we had recently the opportunity to present to your research down here. But essentially what this instrument does, it literally takes a sample of plastics. You know, plastic is quite a topical issue at the moment, especially on the waste appropriate time. Literally burn a piece of plastic in a TDU, or thermal developing unit, extract the gases, analyze it, and then characterize them in a very short space of time. This instrument is the first of its kind that actually deployed currently now in South Africa. The other two are being deployed in Europe, but this one is the first one that took off and Prof. Titus Ngani being honored with a grant from the On the right-hand side, I have the University of Stellenbosch staff, together with my colleague Alexander and Antonio from Cape Town. And the unique value, the unique property of this particular instrument is they do scent analysis. So attached to this GCMS is a olfactory sensor. So as the sample comes through, you start smelling, especially the wine and the special bouquets of the wine, be it cinnamons, and then they are subsequently noted electronically. And as the peaks come through the gas chromatograph, you confirm those kind of observations. So back in the day, you have about 6 to 8 people in the morning coming in and doing the nose sniffing or testing on gin, wine, or brandies. So now you can scientifically say, yes, that does contain cinnamon, and here's the proof for that. But there's another unique combination of instrument that we have down at the Cape, and that I believe is also by the NRA grant funding. So there's another opportunity. Getting together, for example, on the Eastern Seaboard, scientists of ilk. And I mean, we've had a wonderful talk by Prof. Riva Prasad, and he certainly stands head and shoulders amongst the academia. Together with other academia, either GBT, KwaZulu-Natal University, and have a joint application, and maybe decide on where the home for the instrument will be, and decide on what suite of instruments you need to go forward, because clearly that's going to be a resource going forward to handle and manage problems going forward. And it will come from not just us as a supplier, a wide range of people with specific special technologies. Right, let's see, how's my 10 minutes going? So just by way of a snapshot, we have a presence across 25 subsidiaries across the world. We service and have factory trained engineers in South Africa. We have offices in Palito, Cape Town, and Johannesburg. In the sciences, we're quite active. You'll see R&D, petrochemicals, nanotechnology comes up there, catalysis research. On the food and product side, we have food and fragrance. We have systems that are geared towards identifying flavors, identifying fragrances, and undoing or demystifying or deconvoluting what the components are and showing you exactly where they sit. Just looking at some of your products that are produced by your students here. I see there's an interesting project for producing an oil, which got a high level of stearic, palmitic, and yeah, which is quite interesting. I was just tapping to the crop there. So let's now here's a practical local example of a product that you can take to the next level. And also note that your students coming up using these instruments and this level of technology are now producing papers. And often once the instrument's in place, you start attracting partnerships. Other people would like to use your instrument or develop research topics. So that increases your productivity and other rating that Prof was talking about from your over time group. Yes, visibility. And you're improving that. Your students coming out from STM head and shoulders on par with this group. Yeah, that's the team top left-hand side. Richards Bay, I think it's K's diner out on the wharf there. Jacob Van Beek, our managing director. On the bottom left is Alexander Wade, who looks after our separation science. Dr. Christina Kanigadu, a recently employed application specialist from a local university here in KwaZulu-Natal. Antonio Forbes looks after our Cape Town branch, and France and Atta looks after our desk in Johannesburg. Just by way of, I want to say to them, I must introduce you to the people that we visit. So there you go. Thanks, Nico, very much. Thank you very much.
Thank you. Yes, Prof. Brown, you already received something like a framework from what he was for networking and collaboration as well as partnership, because I think that's what he started with Mrs. Fechi, just to give us how the conversation that occurred actually led into these thinking that have been actually shared with us. So I think it's something that to just look into it. It's not something that is very new, but I think that's what we're saying, that innovation is not about starting from scratch. It's about finding what are the gaps, and then you improve, and then you bring something that you can work better. And I think going back to Mr. Manana, that part of now saying, how do we bring the youth back to be interested in agriculture? These are some of the ways that actually now the university can take on in improving the facilities, equipment, and being current, and also collaborating with other institutions in order to make it work. So I think now, I'm running out of time. Sorry, Doc, for being the last one. But let me introduce you. Dr. Kevin Hendrickson obtained his PhD in polymer chemistry from Nelson Mandela, close to my home place, University formerly known as Port Elizabeth, University of Port Elizabeth, in 1999. He remained in academia for a few years, where he published in international polymer journals and presented his student work at academic and trade conferences. Over the course of the last 20 years, he has worked in research and development and technical development roles in various specialty polymer chemical sectors, including rubber, emulsions, paints, coatings, and textiles. The various markets and positions allowed him to gain extensive experience in all aspects of applied chemical manufacturing, from concept to commercialization. He was part of the Scott Bader Global Nanocomposite team, where he was involved in the design and incorporation of nanoparticulates into emulsion technology. He is passionate about the environment, and much of his time is based on developing greener products based on sustainable raw materials and manufacturing processes. He is currently the managing director of Resource Link Coatings in Devon. In his spare time, Doc enjoys long distance running and being in the outdoors. The stage is yours, Doc.
Thank you very much. Firstly, to the Mini-Zulu, thank you very much for the opportunity to be here. To Prof. Brown and your team, thank you very much. It really is an honor to be part of this collaboration. Also to the academics, thank you very much. To the students, you are our future. So thank you very much for being here. I think it's a really important thing that the university is doing this, to allow you the space to see how we can grow our country and our economy. And then also to the industry colleagues as well. It's great to meet all the industry colleagues and to take this further. So thank you very much. I think from my side, we very much involved. Well, firstly, let me introduce our business. Business is Resource Link Coatings, as Prof's already mentioned. And what we involved with, we do technical textiles. And what is a technical textile? A technical textile is any sort of textile that you change the functionality of that textile. So it's changing from a basic, maybe a clothing that's a plain textile, and we add something to that textile to give it a technical property. So we're manipulating the properties of the textile to give it some sort of functionality. And that could be anything. It could be water repellency, so that water doesn't go. It could be for sweating, anti-wicking for your sportswear. It could be that sort of stuff. And that's the sort of field where I play in, or where our business plays in. I think from a research and development point of view, I would look at us being in the latter stage of the research and development, moving from the pilot plant or pilot studies going into the commercialization. So that last little section we spoke about. And I think Prof. Brown mentioned it yesterday, and Mr. Manana mentioned it today, about that sort of helical approach to R&D, about how it is important to have that customer, how it is important to know what is that end user actually needing, and how we're going to take that product to make sure that that end user is going to get the right product. And that's sort of advancing the science, taking the concept or the classical chemistry or classical research that's been done at the university and moving it into the public domain, into the public arena, that's going to add value to the research. So that's the sort of place where we're playing. It's more on that pilot to commercialization. And maybe, I know, thank you very much, I am the last one to talk today, and I know everyone's probably drowsy and wanting lunch, but if you just allow me a few minutes just to give some of the insights that I've had in developing in technologies and innovation. And I think they were up there yesterday. You can see these banners here, outside here. We would have believed that 25 years ago, that was our company's patent, global patent. The patent has now elapsed since then, and that's why you see it all over the world, wherever it is. That teardrop banner there has been on the North Pole, it's been on the Great Wall of China, it's been all over America, it's traveled the world. In the first 10 years of that patent, we've probably fought more law cases than ever, trying to protect the patent, but subsequently the patent has now expired and it's gone into the global market. But if you look at that teardrop banner standing, just flapping in the wind there, all you think it is a piece of fabric that's been printed, that's on a pole. If only you knew the innovation that went into that. And I'm not talking about the design of it, I'm talking about from a chemical point of view, the innovation that has gone into it. And if you just give me some space just to talk about the printing side, if you look at this behind us, I guarantee these are our fabrics that have come from Durban. I can almost be 100% certain that these are our fabrics. We wouldn't have printed them, but certainly would have been developed in Durban. But if you look at that teardrop banner flying in the wind there, a couple of things that from an innovative point of view is, how do you go about developing it? And if you look at the printing, it's been digitally printed onto that fabric. It's a piece of polyester, which is a type of plastic that you were talking about earlier on. And what they've done is they've wide format printers. So if you, I'm sure you've seen these printers that go right across. They're probably 1, 2, 3 meters wide, and they print across where they come back, and they print across, and they put that ink down. But they're sending pictoliters of ink onto that fabric. And if you write with a pen on any fabric, you'll see how the ink just bleeds into the yarn. How do you stop that? How do you stop that? And that's one of the first things that we have to work out. How do you stop that ink from actually bleeding into the yarn? And then you have to go back to all the classical knowledge that we've learned at university. Can be based on charge chemistry. What is the charge of that ink? So can we add something to the yarn that's going to change the charge chemistry of that yarn? That was one of the things. The other thing, what happens is this ink that goes inside, they actually sublimates into the yarn. So it's polyester at 205 degrees Celsius. The yarn opens up, and the ink is an organic particle that's right inside the yarn and gets trapped inside the yarn. But the problem over time, it can start desublimating. Remember, if anyone from chemistry knows, sublimation is direct movement from a gas from a solid state into a gas, and that's what happens. It goes from a solid state with the heat, it goes into gas phase, it goes straight into the yarn. Problem is, what happens with it? It gets wet, you fold it up, suddenly the yarn the color starts moving out again. How do you stop that? The movement of that ink. And there again lies a question. How do you trap different products? We spoke to somebody when they were speaking earlier on about nanoparticles or nanoparticular matter. One of the things that they showed on there is a huge surface area to volume ratio that nanoparticles have. Surely that could be used to trap to be trapping inks. Not only trapping inks, you could use it, you could put it into other technologies. Surely it could be used to trap other particles because of that big surface area that it's got. The other thing that I think that one of the sort of insights that we've got over the years with developing technical textiles is looking at changing technologies. Technologies are always changing. And if you look at the printing technology, it's changed enormously. In the past, you only had dye sublimation. Now you've got latex inks you can print with. You can print with eco-solvent inks. You can print with pigment inks. But each of them have got different characteristics. So you're having to constantly look at what is the customer wanting? How are we going to adapt our new technology to fulfill their properties? And I think one of the biggest takes I can take from that is make sure you partner with the right end user. Make sure you partner with the right technical developer. And so you can go together, because remember, we don't know everything. I certainly don't know everything. But coming together as a team just helps so much more in bringing people together, bringing the technologies together and understanding. Maybe there's one small little thing that somebody says, oh, yes, maybe it's got to do with that cationic charge. And then you can manipulate all your chemistry, you can manipulate your research to make sure that you've got a cationic charge. That's what we've done over the years. We've done a lot with, I'm sure you've heard of HP. HP, the printers. We work with their technical team in Italy, where we've developed quite a lot of stuff with them. Alongside them, many of our technical textiles are HP accredited as well, to make sure that it is in line with that. And then I think just the last thing I'll touch on as well is is legislation. You've always got to be aware of legislation. Legislation is also changing, and especially now in the sort of sustainable space, in worried about health and safety, you've got to be aware of what's happening with legislation all the time. So as much as we don't sometimes like to be reading about legislation, it's important to know when we are developing products that we are in line with what the current legislation is. So things like halogenated products is taboo at the moment. People don't want to know about chlorine, they don't know about bromine. So all your many of the fire retardants that you add to products are halogenated products. So they'll have a chlorine in, they'll have a bromine in. You don't want to go there. And again, perhaps not hear about the nanoparticle stuff. Again, I think there's a possibility for nanoparticles for fire retardants. They spoke about antimony earlier with the nanoparticles. Yeah. One of the big fire retardants is antimony oxide, trioxide, and there again is a possibility, I'm sure, going the nanotechnology route. And again, with that massive surface area to volume ratio, it's going to have the potential to work as a fire retardant will be much, much bigger than a bigger particle size product. So I think for me, it's just to stretch our minds, think outside the box when we're looking at technologies. How can we apply this technology into our technology? How can we apply something that maybe is in water treatment? Maybe what is it about it that's working in water treatment that you can apply to another technology? So that's where I'd like to leave it. It's an exciting place to be where I am, that we are pushing that boundary. We're using some nice elegant technologies to provide some commercial solutions. And you guys, you are future. You are future. Stretch your minds. Stretch your minds. We all in the autumn. You guys are our future. So stretch your minds. But thank you again very much for allowing me some space here. Thank you.
Thank you so much, Dr. I think it was actually an excellent flow, because I think everybody does, and then you just take it and you summed it up, because now you're just taking it from the start, up to just giving us the actual, the how, and the application. So I've got my notes here, my points, but I would like to thank the panel for actually giving us this informative information. Now, I would like to give an opportunity to our industry partner, the postgraduate students who are the future, as well as the online audience, just to ask some few questions. If you can just check for me, let's start with the online while I am looking here within the audience, and I'm going to take some questions from here, but can I check the online if we have any question that has been posted? Nothing. All right, can you please post? I am now going to, waste industry. Okay, the industry, is there anyone who's got a question? Yes, and then yes, and then I'd also like to have I see my colleague here, but I would also like to get the postgrads involved, and then I'll come to you, my friend. Can I start with the industry partner to actually pose some questions to our panel? Yes, sir. Please introduce yourself, where you come from, and then you can now present your question.
Okay. Thank you for the opportunity. I'm Serena Sono. I come from Nyanza Lagos. Explained before, I'm also here. I have a question for you. You talked about the virus application antimicrobial, including the disease treatment. I myself, I explore even anti-agents. So you also mentioned the cons of using the microbial. You're also using the microbial properties and opposed to chemical compounds. But then, as an advice, would you advise young person who explore in anti-agents to really go anti-microbial agents together with chemical compounds for different disease treatment, or would you say, looking at the research and everything in microbiology quite different, would you say should we explore it differently, or do you think there is a possibility to pursue both chemical agents and antimicrobial agents to form one anti-agents in biological treatments? In your own experience and skills and expertise, would you say it is a possibility to link both chemistry and microbiology into this gene?
Thank you so much.
Thank you very much for the wonderful question. For the antimicrobials, remember there is also the power of nanotechnology that has been mentioned. It is under developmental stage where there is the possibility of combining the biological part, like the microorganisms and nanoparticles, to have maybe more impact. But empirical evidence is still being collected.
Thank you so much. Yes, ma'am.
Thank you, sir. Good afternoon, everyone. My name is Zenande Boyd. I'm also from Nyanza. I'm part of the product research and development. And I have a question for you, Prof. So according to my knowledge, in most agriculture industries, they use a lot of chemical fertilizers, which I think has long-term negative effects on human health, crop output, and also damage the soil as well. You mentioned that there's microbial fertilizers. Has this been introduced to the market as yet? Because I think it would be a very good initiative. And what are the nutritional benefits for microbial fertilizers?
Thank you also for the wonderful question. In terms of what is currently on the market, I am not certain, but what I know is there is a lot of research that is taking place regarding that. And biofertilizers are known to be promoted a lot. There are microorganisms that are known to have the potential to enrich the soil and also boost the growth of crops. And what I know is the empirical data is being gathered, but whether it is being taken to the market, I can't give a particular example on that. But that research is quite important. Like you mentioned, it is environmentally friendly when microorganisms are the ones that are used to nourish the soil.
Maybe Mr. Manan, you can also add that you mentioned something about the gap here.
There are products that are already in the market. If you can maybe check around mycorrhizas, you can also look at beneficial nematodes, and many other applications where we've got self-cannibalization mechanism where a certain products are developed such that if a insect or a pest eats that it actually serves a trigger, you know, in the application when you spray it, that is insects that eat on the fruit or eats on that, it becomes sterile, then they don't multiply. It's organic based type of pest treatment that we have in the market already. So they are bio-based products that are available. We can actually
As a follow-up, Prof.
Yeah, I wanted to get a sense, whether, Nyanza is talking about fertilizer. You're interested in the fertilizer side of it?
Nyanza.
No, in terms of the question you asked, microbial fertilizer, did you say something like that?
Yes.
Yeah. So microbial fertilizer is on the market, right?
Yeah, they are.
Yeah, okay. Just wanted to get the clarity straight, yeah.
Okay, Prof. Maluphela?
I think maybe my question is not a question, maybe it's something that can be corrected maybe. I've to Mr. Manana. In your presentation, I've heard that you have mentioned that youth are not interested in terms of agriculture. And also you have mentioned again about the entrepreneurship, but then I think that's where I need to be corrected. That entrepreneurship is not about, it's not supposed to be treated as an alternative. But I believe that it will work best if it is part of the attributes. Because we're in higher education space, maybe attributes for qualifications. And then secondly, we tend to believe that agriculture, or to be involved in agriculture, there must be a huge land. Then we forget that majority of the people that you are presenting to now, they might be living in the city. I myself, I live in the city. There's urban agriculture that need to be promoted for some of us who don't want to get a huge land. So what will be the answer towards what you have mentioned, Agenda 2063, towards the type of information that we share with youth in terms of agriculture and also in terms of entrepreneurship practices?
Thanks, Prof. It's a question that still requires a solution. There are a number of things that perhaps could be attributed to the youth not being interested in agriculture. Agriculture is very difficult. If you plant maize, you leave it outside and you go and sleep in the house. If you have livestock, you leave it outside and you go and sleep inside the house. But then you're expecting a profit, you're expecting a return. And there is a lot that can happen outside there. That's outside your control. It's the soil, it's the weather, it's also pests and other things that might affect your produce. Both crops and animals are affected the same way. So, but the turnaround time from the time you put your seed and the energy that goes into managing that to a profitable product that gives you a return. And the song is one. The primary producers are the price takers. They are the ones who actually feel the brunt of producing food. But where profits accumulate and accrue is at the processing phase and the market and distribution. So where is it that we can make sure that we encourage you to participate in is by looking at ways and means to make agriculture easy. Not as that difficult as it used to. But the patterns are changing. Food production may not necessarily need that vast amount of land anymore. Because we are concentrating, we're looking at intensive agricultural systems for food production. But the challenge at the moment is those systems using liquid fertilizers, and most of them are chemical based. the issue of what you are, what you eat, the long-term effects of chemical-based products is what is going to actually be on the negative side, which is there is a concept currently that we are moving towards of One Health, meaning we have to produce food in a manner that does not negatively impact consumer, which is human. So it starts with food production, the health part, which means if you eat healthy food, you are likely to have less disease burden in the future because healthy food promotes healthy lifestyles, healthy whatever that comes out of that. So we're trying closing the loop on all of that. When we develop fertilizer, we develop insecticides, pesticides, we develop vaccines for that matter, and even any other supplementary products for our livestock or for any of our crops, we need to go bio-based now because we are limiting the effect on human consumption in the future. So our food itself, we must grow it in an organically kind of fashion, but that one also is very costly because the numbers in terms of food demand are quite high. We still have to feed a lot of people, but we must do it responsibly going forward. Look at bio-based means of production. But for the youth, there isn't any way out. We have to make agriculture sexy. We have to make agriculture sexy. I mean, it goes a long way. Even with digitization, that's one way actually to get them back into the mix. We have to actually continue to develop those agricultural technologies that enable food production in a controlled environment. Like now, we have to build high-rise buildings, but as agricultural farms, meaning there are engineering solutions that we have to source and get to the level of how do we artificially develop farms for food production. And one developing area is vertical agriculture, the hydroponics, the aeroponics, and many other forms of agriculture that enable us to move towards that direction.
Thank you so much, Mr. Manene. I think the church, you're also nodding, you would like to add.
Well, talking about making agriculture sexy, I just want to comment on the note from Zenadi there. Not too long ago, I had some time to spend in the States, and on the back of a tractor, they had a near-infrared scanning unit, basically mapping the soil. And now I believe they're using satellite to map the soil. So now what they do is they feed that information into a smart fertilizer unit. So at each specific point, they draw nitrogen, phosphorus, calcium, magnesium maps. And at each specific point, it will use the term early on, inject X amount of fertilizer based on what's required. So it's smart fertilizer. So that's probably the one way, because youngsters love computers and satellite images and all of that. That's probably one way to attract them into the industry. But yeah, to hone in on your previous point of fertilizer, they are going towards site-specific fertilizer. And that reduces excessive phosphorus that runs off and produces your issues on the water surfaces and things like that.
Thank you so much. Thank you so much. Okay, Prof, can I give you first and then two and then yes, 2, 3.
Thanks. Maybe for yourself, around the issue of challenges that come from high level, if you can call it. If you take maybe in the tech industry, it's very challenging to innovate because you mentioned one driver is on your input could be components that you have to source, okay, and where you source them outside South Africa. So if you attempt to design an electronic device and you want to scale it later, you might as well forget it, because if you, in my previous life, of course, you can develop a nice PCB, okay? It's a circuit board, okay? Or even have a prototype for that, to source those components. And for a cell phone, it can cost you $5 to have it inside South Africa. But to place that, it can cost you. So you rather send your designs to China. They place your PCB, they send it to you. So, but that one now is at the government and higher structures. How have you worked on it? Because I'm sure you picked it up. So I'm saying to Kevin, with them doing business here, your inputs, I might suspect to come outside. So how are you managing those dynamics? Was they drive your pricing up? Then the second one is actually a comment for Mr. Chetty to say, even for Prof and his team, to take the recommendation of the technology transfer. Because if you look at the working scenario, is that one of Silicon Valley, where the ecosystem, you bring everyone, all partners, under not one roof now, physically, but the platform that you are talking about. That is where then you are able to access resources pro bono. So if someone does this, I say, well, I have this, I can do it. So it's something that really has to be taken quite seriously. That one of the platforms.
I think, again, for me, it's that development of partnerships, to have the right partners online. So, for example, if you are wanting to outsource manufacture or outsource technology to China or to wherever you're going to be outsourcing it, if you've got that right partner in line, that the right MOUs are all signed up, everything is in place to protect the technology. But then also for me is that it is the right partner that you are dealing with. And that comes with time on how you develop the right partners. It's sort of networking with the right people to create partnerships. And that's why I think it's also so important to go to these outside international, whether it's a trade show or whether it is a academic conference. It's important to get this so you can start developing those sort of partnerships. And then on the second question with regards to the sourcing product from when you're forced to force it, you're quite correct. It is very difficult. And for example, we use a lot of polyester, which is our base cloth, our base yarn for our fabrics. And there is no South African company that makes it, and it's purely based on economies of scale. We cannot make it in South Africa for the same price as you can make in Taiwan or China. They have just got those economies of scale. They've got the entire global scale that they can do it. So unfortunately, we have to be confined to that at this stage. But what we do though is we're adding value to it on this side. So we bring it in and we beneficiating it on this side. We're adding all that value by giving it functionality. So I think that's where that separation comes. And we're actually more competitive at the moment in South Africa than imported textiles. And again, I think also from a government point of view, it's also important that government does protect our industry. And they do have tariffs and duties when products are brought in, whether it's the chicken that we spoke about yesterday, or whether it's textiles coming in, that the country is protected from the import cost.
Thank you so much.
I'm thinking of maybe a simple, crude way of responding. A role.
Yes.
So that we understand investment space and development, how it means. Collaboration cannot be overemphasized. Why? If you want to own a technology 100%, and there is someone who owns a little bit outside that 10%, you own the 90%, he owns the 10% of what you need to make the 100% document. I mean, the product. You actually are sitting on a 90% ownership of zero value. It's useless. So it means we have to get used to partnerships so that your equipment or your knowledge combined with that of that other companies creates a value that you own 50% of what is a billion, you know, type of. So collaboration cannot be overemphasized. The raw way is we can own 80% of nothing. And then you see so we have to get used to the idea of if there is value that sits somewhere else, that engagements. I think put right, we need to actually go outside and see what other people do and try and secure those partnerships. Even if maybe you require 20% of what it does, but combined, the value creation is huge. You may even actually have 50-50 or what have you, but it's what it is. It's the crude way of doing business. You have to actually appreciate and collaborate.
The challenge becomes when you have to meet a localization target. Because then once the value goes outside, it's done there, then you can't account for it. And if it's a government requirement, they want 58%. You can't localization.
Yes, there is those dynamics of what government says. But on the ground, it's something else. You have to put a strategy in place to say you can start here now because most of the expertise sit outside. But in your collaboration arrangement, you can put it up front, say eventually the benefit must go both ways. Let me maybe share a very painful example of why it can sometimes be very dangerous to own 100% of a company which sits outside and you are sitting here. Decisions that happen there can close that company while you are sitting here. So we must not be happy about owning 100% of something that's sitting in a foreign land and those people who sit there own nothing of it. For your security, make sure that you partner with someone local there so that your interests are secured by that person there. And once you are a value to that country, the chances of them saying, shut this license of this telecom company are very minimal because they are also killing one of their own. So we must actually look at collaborations that are meaningful, that are beneficial in both ways. If you engage in a negotiation that favors you largely and less on that side, remember you are tipping the scale that say, if come to a push and there's a crunch period for decision, if he says, I'm owning only 30%, you may as well shut this thing, 70% owned by someone else. That's easy for them. Yeah. But if you own 30% and he owns 70%, you would say, no ways. Just hang on. He will fight for you when we are not there. So partnerships are important, but always negotiate for the future and look at the risk profile of what we are doing. When you are not there, someone else must be able to stand for the risks and mitigate any eventualities. There's not a single company that is not facing the political risk. The political risk is the biggest risk in any business that has no mitigation measure. You can take insurance and other things, but on a business, if there is a riot and they burn the buildings and what have you, in many cases we are very limited. You know, so political risk is the biggest risk because anything like PE is a risk to other people, to other businesses, but it's a political decision. So politics is the biggest risk in many other businesses that has got minimal or no mitigation measures. So we have to negotiate when we do partnerships in the manner that enables that part of the risk.
Yes, just in response to your question, yeah, I would certainly take what's a note, collaboration, absolutely. These are the sort of the early walking stages of this. I think the nodes have to be developed within industry, to have some type of a working forum, and then let's see how that goes forward. Going forward, I like the idea of some kind of a virtual interactive scenario where the contributors can actually interact on a common platform. That's certainly a few yards down the line. But the immediate steps, I think, are to get industry and academia probably around the table. Let's establish the needs, the wants, and then as the classical marketeers say, price, product, and place. So let's just put that into practice and establish our priorities.
Yeah.
Thank you.
All right, ladies and gentlemen, I think this is a very interesting discussion. I think it's taking us somewhere. So I think also the question that has been asked is how do we actually now move from the lab to the market? So I think we are trying to actually provide those answers so that Prof. Brown can actually be able to write a report that is not just black and white, but a functional report. So in that manner, I am just requesting that we continue with this interesting debate or discussion so that we can actually reach our goal. So I'm going to invite you to actually pose your question.
Oh, thank you, Prof. A quick one for Sakia. We people waiting for Young and results, but it's a new company. System dioxide is mainly one of the raw material along those applications. Are you at this point perhaps using any form of silicon dioxide for any of your products? I've heard from Mr. Manana, he's also touching base on the collaboration on the inhibition of working with local producers in order to form that collaboration.
Yeah, titanium dioxide is an incredible product. It's for those of you who don't know, titanium dioxide it's a white powder. It creates an opacity or blockout. So all your white walls here that the paint all got lots of titanium dioxide in to give that bright whiteness to the paint. So whether it's a coating, whether it's a paint, there's lots of titanium dioxide. In the last 3 years, titanium dioxide almost doubled in price. It used to go 40 rand a kilogram, sitting at about 68 rand a kilogram now. So you're in the right space, the right time to get involved. But because the price has gone up so much, people are looking at extenders. They're looking, can they add something else into your coatings rather than titanium dioxide to give it that same sort of opacity or blockout, what you want to call it, or whiteness, but at a cheaper price. So there are a couple of extenders and there's some interesting technologies that have been developed for extenders. But without a doubt, titanium dioxide will not be, it won't be lost in the market. So you are at the right place at the right time for titanium dioxide. And it'll be great to have a South African one because at the moment, lots of it is being brought in from the East. A local player in the market again.
Yeah. Thank you, Dieter. I think the discussion has been quite interesting, and I thought I would just come in. I know you've given me the task of writing the report. But there's some interesting points that some of them I want to just touch on quickly. In terms of my colleague here, but the proposal from Chetty, Mike Chetty. Yes, I mean, we have been having discussion. Chetty and I have been having engagements before today. And some of those things I think that we have discussed, and he's like our appointment to the industry. He's actually, even today, in terms of the industry coming through, is part of that. Already we started to make this up. So that's There's not that it's been something that we've been acting on, and we certainly we need to find new ways of sort of growing it. So that's important. Just to go back to Kevin though, so you have seen that, and I want to take in Malik as well at this point. So you've seen what we can do with our HR10 machine, and as you said, you know, it has a lot of functionality. And by the way, just as a side comment, you know, during COVID, we heard the term gain of function when and then now I hear you using it in terms of textile to say function, the actual textile can gain function. So that's an interesting development in terms of the way you think about textile. But the point is, I think we need to come into some sort of collaboration, because I think you have a lot of ideas that we can actually utilize in terms of our HR10 machine equipment. To say, you mentioned two, one about using it in relation to trapping of ink. And then the other one is in terms of the point fire extinguisher, fire retardant. You mentioned fire retardant. Now, maybe we need a broader conversation out of this to say, how can we bring in Dr. Malik in terms of application of those ideas in relation to these particular areas divided by. Perhaps we can think of others as well, and then the kind of a research we can probably put forward to get you to develop that into some kind of a practical. Maybe you can utilize them in your industry. Maybe you can find other players who can come in. Obviously, you might not get into retardants, but you can identify the right industry there who might be interested in that, and then you can develop a relationship in that way. So, your thoughts on that, and maybe how Dr. Malik fits into that, can tell us, since Nerish is not here. They work together from Nerish, who was talking earlier on. So, yeah, I thought I would throw that in because I want to add that part into my report that I will give the chance to do. Yes.
Yeah, so just to add to that, I think what you were saying there about the trapping of ink, so using the ink as an example, but I think the nanoparticles could be used in a much bigger sense. It could be for water treatment, the tracking pollutants with the nanoparticles. So I think it's a much bigger field than just my direct field. And I think the technology can be grown quite extensively in the market. Yeah, and I do believe, I think the team chart, I'm not sure what nano technology group you have at the university, but it would be good to have a nano group together that we can sit down around a table and we can discuss and maybe get other industry players that have got some ideas or other academics that have got some ideas and start that sort of collaborative direction research.
Yeah. Okay.
Dr. Malik?
Yeah, I would like to thank everyone, but I just want to share one of my experience, like while we were in University of Manchester. So there are some like industrial based projects which we were involved in. So one of the industrial based project was on the increasing the quantum efficiency of the different quantum dots and increase their efficiency. That was one of the spun off from the University of Manchester, Nanoco. Later on, they had like some issues with Samsung as well. So I'm not sure like where are they now, but they the project was based on that they wanted the atom efficient synthetic routes, like in which we can prepare high yield nanomaterials with high quantum efficiency. So another project in which we were involved in was from the British Petroleum. So in the one, what they asked, they came up with the problem, and they said that we want our pipes, the steel pipes which they are using to extract the oil and all that. So they said that let us, I'm just giving you a rough idea. So they said, like, let us say that they rust in 1 year. So what we want is after 1 year, we need to change all the pipes and everything, and it costs us a lot. So is there any way by using some nano materials coating or stuff like this, so by which we can resist their rusting, even for a, let's say, even for like 2 months or 3 months or 4 months, and thereon we can build our knowledge and go on. So that's where we start developing two-dimensional materials like chromium dope, molybdenum sulfide, and we did some research, and it was a quite fruitful research in a way that we did improve some of their properties. So I think it's very good. Like if sometimes it's the industries, if they can like also, if we are able to discuss really some ideas, like what are the needs of the universities, like we have the skills and we know what, but there might be a particular problem with the industry which we are not aware of, unless like there is a better communication between us, and I hope it can bring a fruitful solution to all of it. So that's it.
Thank you so much, Doc. Ross?
Thank you, Professor Kwanisi, and I really appreciate our panelists for enlightening discussion. What you have actually done is to show our postgraduates that the area of research is very wide and it varies, so they have no problem saying they have no research areas they can or topics they can pursue into that. What is, I'd like to know, I may not have the answer to, and what is coming out very clear is that we recognize the problems exist. And there is that way of turning these problems to opportunities, which are the research opportunities. The question now comes, what are the challenges that are hindering the researchers in taking up these type of opportunities? Could it be lack of capacity? Could it be lack of funds? Could it be lack of policy guidelines? Or could it be misplaced priorities? Or what could it be that we can have this collective approach in addressing these problems, which will turn out to be the opportunities? That's I just wrote to all of you, not to any specific person, but I would like to see the thoughts that we have around that. Thank you.
Ralph, would you like to start? Maybe from your own perspective as an academic. Pushing me the button.
Thank you for the question, but actually it is also because I think the challenge can be multi-faceted. Ranging from many issues, whether it's I'm try constraint to time can be included in there, but I think it is a very complicated issue that is to that. Because I'm sure from a theoretical point of view, as a person does research and related, they can actually tell the gaps that this can actually be converted to that, that can be converted to that. But I think it's multifaceted way many people don't do it. Like if you look at microbiology, so one of the widest areas, like I indicated one, and we can making biofertilizer, because microorganisms are found everywhere. And one can just look at different environments. So microorganisms can also be used for bioremediation in the environment. There are microorganisms that are known to produce chemicals that can break down worms and clean the environment in a friendly way. I think the reason that people researchers don't go into it, I think they're complicated. I think they're complicated and maybe they need to be. But I think academics working in different research areas, they can on a day-to-day basis know that okay, if I kind of organism is doing this to the lab there, and this can be turned into some information. But I think it's very complicated why then people don't take this up, and maybe in a different forum that can actually be discussed. Why is it that people don't take these ideas to market?
What my colleagues here, Prof. Brown and Prof. Mabusela, they want to take on this question.
No, I think the simple answer for me is a question of where one chooses to look. I mean, historically, academics, and that's why I say, you know, that historically, academics have taken the easy path of looking within the discipline for problems. And looking within the discipline means you want to develop knowledge. So you look within the discipline and say, oh, I need to expand knowledge. I'm concerned about what is going on behind outside in the field, or like I said, beyond the wall of the university. I have a colleague who used to call universities intellectual ghettos. And the reason for that is that the walls of the university become the limits of the university. And we talk about the ivory towers and the elite universities, and so they're just concerned narrowly within the discipline. Disciplinary boundaries have forced academics to concentrate too much on wanting to expand knowledge. And so Burton Clark, as he said, research is not an end in itself, it is for something. And he said we should sell that to industry. Burton Clark from UCLA, US. That's where this idea of innovation sort of exploded to say, let us focus on getting industry to utilize that knowledge and look to industry for problems and look to the community for problems. In other words, look beyond the walls of the university. So the moment and that's why we want, look at our exhibits. Why don't we have all the researchers? We have more than 120 researchers here. And out of this, we might have, how many? Less than 20 exhibiting. Where are the others? And because we still have the emphasis on looking within the discipline. And that's what we're trying to do. That's not a fact. That's why I say he knows. He knows the answer.
Thanks, Prof. Prof. Mabusela.
I was agree with Professor Brown, but however, I still have just something to add on. I'm from the city, I'm from the biggest township in the world, Soweto. And I normally, when I go home, see these people, pushing a lot of trolleys with waste. The waste management, the waste, working landfill, but waste is taken from household in Soweto to a landfill. And then from a landfill, people coming in to take recycled material to sell or recycle, while it would have been the very same municipality to take the very same thing to incineration or to recycle or to whatever point. Ourselves, as Professor Brown has said, we focus on our specialization. We don't want to solve a real life problem doing research. First of all, that landfill, immediately when they come in and dig it, a lot of plastic comes out, a lot of plastic cause havoc, animal eats those plastic and all those things. Meaning the same thing that can be solved or controlled. There's no any policy, there's no any. We're afraid to confront situations because we're afraid to be targeted, but we say we are researchers. We're afraid to also even solve the issue of what we call the environmental, sustainability, environmental havoc, also diseases, also because when the rain comes in, there's erosion, it goes back to the very same household. And then most of the time, we always say that if I publish this, newspaper people come and interview me and whatever. I think one of the challenges is lack of policy, lack of access, lack of ethics, lack of information. Immediately when you do those kind of research, somebody will close the door because you will still need permission to do some of these researches. Then somebody will close the door, which will expose lack of responsibilities among some managers. I think that is one of those issues. Yes, academic freedom.
You can research anything. I'm actually against that. Academic freedom says you research without fear or favor. You don't worry about who's political is going to come and say this or that. Yeah. The moment you can start taking that line, you become political yourself as an academic. You have to, anyway.
Maybe from this slide, can I just now throw it into the post-grade?
Yes.
To just hear their views in regard. So what do you think about this so-called income-wearing approach? How does it affect you as the future researchers? One person.
They feel constrained. Where do they look for, where do you look for problems? In the subject?
Are you free to actually bring your own thoughts, or you find someone already telling you? So where do you find your research problems? Anyone? Anyone online? Okay, all right. Okay, there's a question here.
Let me try.
All right.
It's a very difficult question. And I don't want to sound like I know, it's not an answer, but it's a very difficult question. It's a difficult question. I think from a presentation from Prof. Malay, he stratified two parts. And said there was an applied a component of research and the basic. So sometimes we don't have to take away the liberty of academia on blue sky research, because we don't know what we don't know. So if we limit that, then we're going to get stuck. We're going to get stuck in that old cell phone that only can talk outside. So we must not limit blue sky research. It's only a matter of prioritization. Blue sky research for me, for academia, must form 80% and 20% of the energy on applied research. Because we are taking away generation of new knowledge. So which means one opens up the can and says, what then does it mean to the products that come out of the university? The university must be prepared to release some of the PhDs to industry. That's what it means. Not hold them and keep them here, and for blue sky research only. You must produce as many so that there's a good balance of research, work, and capability that's outside the industry to complement blue sky that comes up for application purposes. In balancing out what the core business of the university is, I think there was that part that talked to applications as the biggest driver for the university. Can't stop that. But we must manage the outputs in terms of the intellectual property that's military. Because you don't want to compromise. Which means the university has a big decision to make. Are you in the business of selling knowledge, or in the business of selling products, or in the business of starting up companies? That's where you have to actually entangle. Because then if you want to be everything, then there's going to be a problem in that the university is going to end up competing instead of taking its rightful space of selling knowledge to the next people who are able to take it further and apply it. And then get the necessary money back into the university coffers, just from generating new knowledge and selling it. And then you are actually in the rightful space. You don't expend yourself too much to engaging in the space of startups and up to commercialization. What are you doing there? You know, in fact, for me, you should already be pipelining your ideas to the level that at a certain incremental stage where you see the capability sits outside, you say service, put up a compact and put up a big box of all your technologies that you've demonstrated, you've actually developed, call industry and say, come here, here's a portfolio to look from, what are you interested in? Then you sign the papers, you sell the knowledge, it's gone. And at some level, where I actually touched on saying, we don't want to leave universities to their own devices. The future that sits out there on partnerships means somehow there has to be a collaborative arrangement at developing interventions for the country for how to deploy the technology or knowledge in an impactful manner. There are actually means to actually do that, which is driven through collaboration, meaning industry is prepared to do what is called joint project development. Joint project development means there's someone who's an expert who's coming with an idea or knowledge. There's someone who has the money. There's someone also who has the market for the project. And they jointly develop this to minimize the risk. So that it means you don't have to sit in the corner there and develop the whole concept alone in hope. And unfortunately, hope is an inactive way. You just hope, do something, collaborate early, and do something that already you've got a partner, and all the risk has been minimized, and then it's ready for presentation and out there into the market. But you collaborate early and set the boundaries up front. But that part of competitively where the university is positioned in terms of the IP development, there is a certain stage where the university must draw the line and say, we're only moving from here to here. After here, service license. Or explore other ways of doing it so that you get the good value for what you are doing. But also, I think on the side of the students, they still need papers. They need those gowns. They need those certificates, to show that they are actually what it is. So it's that competitive arrangement. What we really want to be. But many of what we must also check on the list of billionaires or whatever, people who are rich, who have taken the course, some of them don't have high qualifications, but they are actually strong on the entrepreneurial side. So which means we'd have to find a way of marrying the appetite for business and the appetite for pursuing technology. So that even people outside, the students that are sitting outside in the finance field, economics and HR and what have you, some of them can actually be the buyers of this technology. They are the ones who can actually see opportunity and take it and drive it to success. It was developed by a scientist, but also taken out into the market by an HR practitioner. Because that's what he sees, and that's what he tries. That's what he's got passion for. Because entrepreneurship is not about money, it's about persistence. Persistence to actually be able to, and no to you means knock at the next door. Doesn't mean stop. So we need to encourage such that.
Thank you so much. Yes, let me just get this last one and then
Thank you, Mr. Malan, coming in the rescue of the postgraduates. They say silence is golden and rules the place. It's a question of the speech that you made also to the question I was posed to the postgraduate We talk about the youth being not interested in agriculture, which I said is not the only fact, or is not the only sector whereby the youth is not interested in certain development. My question is, you also mentioned, Dr. Raleigh, you also mentioned about the Ukrainian Russia war, of which it has got a wide impact. It can also impact the country, even if it's with it's into the larger. And then you also mentioned certain factors that is taken into account for their award and second. It's just to ask a question: what interventions has been implemented to bring the youth to engage in such conversations, to bring the interest of them to understand that not only what is in front of them can only affect the socio-economic effect, but also everything that goes around to this country can be affected in terms of economic and everything. So what interventions has been implemented, or are they yet to be implemented? If they are, how are they advertised? How do you bring youth to begin to in such conversation, engage, bring ideas? Because in a matter of knowing the youth that I am, we can have ideas, but how we are approached and how we are being invited to conversation can be different. So the question is, you as a university and working in collaboration with different companies, industry, other institutions, what interventions have been placed in this, or is there a plan to bring such interventions into play for us as postgraduates or any undergraduate, even high school, when they come into contact with academics and everything? Idea of solving problems, bringing back to lab to commercial, because the commercial problems comes back to the lab, we solve it, it goes back to it's like a cycle.
Thank you.
Interventions.
You want to know this? I don't know. I don't know. I really, to be quite honest, it's a loaded question and it's a very difficult one. Look, there are a lot of youth interventions, but this, what I was talking about is just but one part. Remember that from where I am sitting, money is no longer a problem. It's about ideas and opportunities that have a real meaning. The ideas that have a real meaning. There is money. You know, if you apply to ITC today, there is money. If your idea is good and flying, they will give you money. You apply to TIA and there's an idea that flies. We are looking, there's someone looking for a solution like yesterday. There is money for that. So money is no longer an issue. It's about ideas that are able to drive impact that we are looking for. There's a reason for that. It's because we funded a lot of ideas that are very expensive to invest in, but they end up in a concentrated arrangement where it's just one project sitting there in the corner that is not able to scale as we hope for, because it's only dependent on one individual. Hence, our approach is changing, putting money at universities with an aim of amassing a lot of IP and knowledge development that we can influence, not necessarily instruct, that we can influence to commercialize in a particular direction that ensure much bigger impacts. If I'm making an example, if there is technology that operates somewhere and it's on a large scale, and the university sources an expert who miniaturizes that technology, and the technology is able to be distributed to communities to make maybe good flour from sweet potato and what have you, and make a derivative type of product, and it's franchisable. That means it can be rolled out and it's not limited only to one company. Why not we actually look at such kind of interventions? So money is not the issue. It's about ideas. And even those ideas, if they are good, it's about the impact that we will draw from it. That's what we are trying It's not really the money issue. It was a very difficult question.
It's a PhD question. Thank you so much, Prof. Allow me to thank the panel for really giving us this information and very live discussion. Thank you so much for sharing the knowledge. I think, Prof, it's just for me few points because I think the question is not answered in detail. For me, it's just points, the bullets. I think the panel sort of indicated that into our traditional research, we need to add this importance of engaged research and be able to describe it, what is the meaning, and be able to share with our students as well as the researchers, because it needs to start with the researchers so that the researchers, they understand the academic freedom and the value of actually now addressing problems that go beyond that university. So I think the innovation component, like we were saying, Prof, there are so many researchers, but there are very few who are participating in innovation. What is it that we are doing? But then I think from the panelists, they say we need to make science real. I think that's what Professor Madoroga was also sort of trying to elaborate and everybody else. But then I think the question was, when you are making this science real, the university needs to take a certain position and know what they are actually trying to do, so that they do not step into other boundaries where they can actually give to other stakeholders to actually run on behalf of the university. Because we need to understand that the agenda and as well as the purpose of the student is here for a certain period of time and then they move. But at the same time, whatever they are doing, it needs to make sense and be problem-based so that it can actually target end user. And then also to make sure that the research that is being done, it brings a transformation. Also, it was very emphasized that we need to be relevant and our research has to be aligned. And in that, when you are relevant, you are and also aligned, you are able to identify and pick up the stakeholders and the collaborators as well as their partners who are going to be now supporting and complementing your purpose. And that can only be done through networking. And I think this is where now it goes to that technology transfer framework. Is it platform, technology transfer platform framework that was presented. And it was emphasized that if you actually set that kind of a system, then it makes your life much more easier, as well as it reduces the risk, which we don't want to find ourselves in. And then also, you need to partner with the right user. So you can have the collaborators and all that, but you need to also partner with the right user. And then you need to be aware of the legislations around you, because that can also be a hinder. And then I think the most important thing is, let us be forward thinking. We cannot think in front of our foot, because it's not about today, but it's about the future. And for us, we need to make sure that, I am quoting you, plagiarism here, Dr. Hendricks, let us stretch our minds. And I think it goes back to the quote that I took from you. It's the agenda has to go beyond the university in order for us to make a difference. Thank you so much, Professor Brown, and thank you everyone. Thank you.
Oh, okay, finally, we can respect your name now. Thank you very much. So I'm gonna give you gifts now. I have this that how do you want me to do it? How do you want me to do it? Right here. Yeah. One by one. Give it to them. Yeah. Okay. Let me start here. So like this, how do I look at the okay, just give me all of them. Oh, that one. Okay. Yes, I think you kind of move on. Okay. This is the we have to go according to the rule. Is it okay like that? Yeah. Standard is okay. Okay, look at the camera. And smile. Continue smiling. There you go. Thank you. Thank you. All right. Okay, that's it. Yeah. Thanks so much. All right, let's go.
Thank you.
Okay, we're done then.
All right, ladies and gentlemen, there's something that is exciting here, right? Prof. Brown came prepared. There are gifts from the research and innovation. So I am Professor Moyo now. So I'm going to touch it, shake it, shake it, shake it, shake it, shake it, shake it, and then cross fingers that I pick your name. Right? If your name starts with N and your surname Z, not over
Just one step this side. Right. Yeah.
Okay. Right. Okay. Mbele.
Okay, can you show the logo?
Which one? This one or this one?
Right, thank you. Continue. Yeah.
Okay, right.
Okay.
Tesfaye, Tesema, Gitamo.
Right. Right, perfect. Smile and look at the camera. 1 and 2.
All right. Thank you. Okay. How many? 2. Okay. Ayanda Bata. So I guess this side it was excluded.
Okay. Ayanda.
Bata.
Okay, 1. The last one.
Thank you. Last one. All right. Yeah. Hey. 1, NK, no wonder, Kondo way.
The logo. Right. One and two.
All right, thank you so much. All right, bro, is it finished now?
Now you
Okay, all right, thank you very much.
When you were talking about technical, there are not the microbiology. What can I think about it. I think I'm actually going to read about it. Yeah.
You follow the principle. Once it's done here, and then there's the other side. There's no division, so you can do